Hello there, and welcome to Just About Earth, where curiosity gets cozy, deep time slows down, and science takes the long, scenic path towards sleep. Tonight, we are travelling so far back in Earth's history that even the word ancient begins to feel a little underdressed. We are going to a world before forests, before flowers, before fish, before insects, before shells were common, before bones had really taken up their long career of making paleontologists very happy. We are going to the Ediacaran Period, a stretch of time more than 500 million years ago, when life on Earth still looked so unfamiliar that, if you could somehow lower a lantern into those quiet seas, you might think you had arrived on another planet entirely. There were no dinosaurs here, of course, no trilobites yet marching around like tiny armoured accountants, no coral reefs crowded with darting fish, no seaweed forests swaying in the shallows. Instead, there were soft shapes resting on the seafloor, quilted bodies like flattened cushions, fronds rising gently from the mud, circular impressions like strange medallions pressed into stone, and living forms that seemed to hover somewhere between animal, plant, fungus, and something we do not have a good word for at all. So before we step into that dim prehistoric water, let me ask you something. Where are you listening from tonight? Are you tucked away in a room where the day has finally gone quiet? Is it late where you are, with the windows dark and the clocks doing their little glowing duties? Or are you somewhere where morning is beginning and the world outside is still stretching itself awake? It is a curious thing to sit in our modern rooms surrounded by lamps, phones, blankets, books, and perhaps a cup of tea that has gone slightly cooler than intended, and think about a time when none of those comforts existed, when Earth itself was still learning how to host large life. And yet, here we are, with our warm houses and restless minds, looking back through more than 500 million years, trying to understand creatures that left no bones, no eyes, no teeth, and no dramatic footprints across a muddy beach. Just impressions, shadows in stone, a few delicate clues that survived everything. If you find this kind of journey soothing, intriguing, or simply a pleasant way to let the day loosen its grip, I would be ever so grateful if you gave the video a like and perhaps subscribed. It helps this quiet corner of science reach others who may also enjoy drifting through Earth's deep past at a civilized pace, rather than sprinting through it like a caffeinated ammonite. And as always, I do hope this story is interesting enough to keep you company, but not so exciting that it keeps you wide awake. Though if it does, at least you will be lying there with a head full of ancient seafloors, soft-bodied mysteries, and the comforting knowledge that life has been strange for a very, very long time. Now settle in, let your thoughts slow a little, and imagine Earth before it became familiar. Not Earth with birdsong, grass, rainforests, or the distant rumble of mammals moving through the night. Not even Earth with scuttling crabs, swimming fish, or anything with a face that might look back at you. This was a planet still recovering from extremes. Before the Ediacaran, Earth had passed through some of the most severe ice ages in its history. Episodes so vast that scientists sometimes describe them with the wonderfully dramatic phrase snowball Earth. It is not quite the cosy image the name suggests. There were no cheerful snowmen, no scarves, no one saying, "Isn't it crisp out?" over a mug of cocoa. It was a planet gripped by ice on a scale difficult to picture, with glaciers possibly reaching far into the tropics, and oceans sealed or nearly sealed beneath frozen surfaces. For living things, which at that time were mostly microscopic, simple and marine, it must have been a long and difficult chapter in the planet's story. Then, slowly, the ice retreated. The world warmed. The oceans opened again. Rivers began carrying minerals from newly exposed rock into the sea. The chemistry of the planet shifted. Oxygen, though still far below the levels we enjoy with every sleepy breath tonight, became more available in some environments. And in those changing seas, life began to experiment. Not with speed, not with claws, not with sharp little jaws or the bold ambition of chasing someone else around for dinner, That would come later. The Ediacaran was quieter than that. It was a time of bodies appearing where bodies had rarely been before. Larger, softer, stranger bodies. Life began spreading into shapes that were visible to the naked eye, if there had been any naked eyes around to see them, which there mostly were not. The audience had not yet evolved. It was like a theatre opening before anyone had invented tickets. The Ediacaran period lasted from about 635 million years ago to about 539 million years ago, which is a span so large that the human mind tends to politely set it down and back away. We are used to thinking in years, perhaps decades, if we are feeling ambitious, maybe centuries when considering old buildings, old kingdoms, or a family recipe with suspiciously vague instructions. But tens of millions of years are not really something we feel. They are something we have to imagine by comparison. The entire history of humans is just a tiny shimmer near the very end of Earth's timeline. Dinosaurs, impressive as they were, arrived far later than the Ediacaran. Even the Cambrian explosion, that famous burst of animal variety with claws, shells, eyes and all sorts of evolutionary enthusiasm, had not quite begun. The Ediacaran sits just before that, like the dimly lit room before the curtain rises, filled with odd shapes waiting in silence. The name Ediacaran comes from the Ediacara Hills in South Australia, a place where some of these ancient fossils helped reveal that complex life existed before the Cambrian. That may sound straightforward now, but for a long time it was not. The fossil record seemed to burst into recognisable activity in the Cambrian, with creatures that looked much more like animals as we understand them. Earlier rocks were often expected to be nearly empty of large life. So when paleontologists began finding these strange impressions in very old rocks, the question was not simply, what species is this? It was more like, what are we even looking at? Were they jellyfish, sea pens, algae, failed experiments in animal life, completely separate branches of living things that bloomed for a while and then vanished without descendants? The Ediacaran has a way of making confident labels quietly leave the room. This is part of what makes it such a wonderful topic for a calm evening. The Ediacaran world does not rush toward easy answers. It does not hand us a tidy cast of characters with names, habits, and familiar faces. Instead, it offers impressions, outlines, surfaces, textures, and possibilities. A fossil like Dickinsonia, for example, looks almost like a ribbed oval mat, sometimes compared to a quilted pancake, though admittedly a pancake from a kitchen with very unusual ambitions. Charnia resembles a frond, rising in a branching pattern that once made people think of sea pens, though its exact place in the tree of life remains debated. Some Ediacaran fossils look like discs, some like leaves, some like tubes, some like wrinkled bags. Some appear so unlike modern organisms that scientists have suggested they may represent extinct ways of being alive, entire designs that Earth tried for a while and then set aside, rather like a first draft written in the margin of evolution's notebook. But we should be careful with that phrase, first draft. It can make the Ediacaran sound like a rehearsal for the real show, as though these creatures were simply waiting for the Cambrian to arrive with better costumes and a more confident director. That is a very human way of thinking, and not entirely fair. The Ediacaran organisms were not trying to become anything else. They were living in their own seas, under their own skies, in conditions that made sense to them, or at least to whatever passed for making sense when you had no brain, no eyes, and probably no strong opinions about the weather. They were not primitive in the way we sometimes use that word to mean clumsy or unfinished. They were suited to a world that no longer exists, and that world, to us, looks alien because we are used to life after the great animal inventions had taken over. Imagine standing somehow on the edge of a shallow Ediacaran sea. You would not hear gulls. You would not see shells washing onto the shore in bright fragments. You would not see crabs sidestepping indignantly away from your feet. The land behind you would be barren by modern standards, with no trees, no grass, no flowers, No roots gripping the soil, perhaps just bare rock, sediment, and microbial life doing its quiet work. The continents were arranged differently. The air was different. The ocean chemistry was different. Even the colours may have felt wrong to modern eyes. And below the water, across mats of microbes that coated the seafloor like living film, soft organisms rested, grew, absorbed nutrients, filtered, grazed, or did whatever peculiar form of living their bodies allowed. It was not a reef. It was not a meadow. It was not quite a garden, though people often reach for that word because gardens are peaceful, and the Ediacaran often seems peaceful from this distance. But it was a living surface, a textured world of soft forms in a sea that had not yet learned to be crowded with teeth. Those microbial mats are important. Before animals became busy burrowers, grazers, and sediment stirrers, the seafloor could be covered by thick communities of bacteria and other microbes. These mats helped stabilise the sediment, almost like a sticky blanket over the ocean floor. For soft-bodied organisms, this may have been a very useful place to live, and, by a remarkable bit of geological generosity, a useful place to be preserved after death. Later animals would churn the sediment so thoroughly that this kind of preservation became much rarer. But in the Ediacaran, the seafloor could hold impressions with surprising delicacy. A soft body could press into the mat, sediment could cover it, minerals could do their slow work, and hundreds of millions of years later, a human being with a hammer, a notebook, and perhaps an unreasonable tolerance for sunburn could split the rock and find the ghost of a creature older than bones. There is something humbling about that. These organisms did not leave behind skeletons like dinosaurs or shells like ammonites. They did not roar, bite, leap, or pose heroically in museum halls. Many of them were flat, soft, and quiet. Yet they changed our understanding of life's history. They told us that before the world became noisy with animals, it had already become strange with bodies. Before claws and eyes, there were quilted forms. Before predators turned evolution into a rather stressful arms race, there were communities living across mat grounds in ways we are still trying to understand. The Ediacaran asks us to lower our expectations of drama and pay attention to subtler things, a wrinkle, a branching pattern, a repeated ridge, a faint oval in sandstone. It is paleontology at its most patient, and patience fortunately is very welcome at bedtime. Of course, calling these organisms alien is not to say they came from somewhere else. There is no need to invite flying saucers into the Ediacaran, although one suspects they would have found parking easier back then. They were Earth life. They belonged here as much as oak trees, octopuses, mushrooms, and slightly confused houseplants belong here now. But they were alien in the sense that they do not fit easily into our mental categories. When we think of animals, we tend to imagine mouths, muscles, nerves, eyes, legs, fins, or at least some clear sense of front and back. Many Ediacaran organisms seem to ignore those expectations entirely. Some had no obvious head. Some had no clear organs. Some show patterns of growth that are difficult to compare with living animals. Others, perhaps, were closer to animals than they first appear. The puzzle is not that they were impossible, but that they lived before the familiar rules had fully settled in. That is one of the great pleasures of deep time. It reminds us that the present is not the default setting of the planet. The world did not spend billions of years trying to become the one outside our window. Earth has been many Earths. There was an Earth of lava seas and bombardment, an Earth of microbial oceans, an Earth locked in ice, an Earth of soft quilted organisms resting beneath shallow water, an Earth of trilobites and armoured fish, an Earth of coal forests full of giant insects, an Earth of dinosaurs, an Earth of Ice Age mammals, and now this Earth, with us in it, listening to stories in the dark and wondering how anything as improbable as life ever got going at all. The Ediacaran is one of those earlier Earths, distant enough to feel dreamlike, but real enough to have left fingerprints in stone. And the fingerprints are scattered around the world. Ediacaran fossils have been found in Australia, Canada, Russia, Namibia, England, China, and other places, each site offering a slightly different window into those vanished seas. Some preserve deep water communities, some show shallow marine settings, some capture entire surfaces where organisms seem to have lived together, almost like ancient snapshots of a seafloor before it was sealed away. The famous fossil beds of Mistaken Point in Newfoundland, for example, preserve communities of frond-like organisms in fine detail buried by volcanic ash long ago. The White Sea region of Russia has revealed beautiful examples of Dickinsonia and other forms. South Australia remains one of the great places for understanding these organisms, not just because of the name, but because its rocks preserve extraordinary bedding surfaces, whole neighbourhoods of Ediacaran life caught in geological stillness. It is worth remembering how unlikely any of this preservation is. Soft bodies usually vanish. Anyone who has ever left lettuce too long in the fridge understands, in a small domestic way, the problem of soft tissue preservation. Now imagine expecting a delicate, boneless organism to survive not for days, not for years, but for more than 500 million years while continents move, mountains rise, rocks are buried, heated, cracked, lifted, eroded, and eventually noticed by someone walking across an outcrop. Fossils are not guaranteed messages from the past. They are rare accidents, and Ediacaran fossils are especially rare kinds of accidents. They are whispers that somehow made it through a storm. Tonight's journey will move through that world slowly. We will begin with the planet itself, because the Ediacaran cannot be understood without the ice that came before it and the changing oceans that followed. We will drift across microbial seafloors and meet the soft shapes that lived there. We will look at the famous fossils that still puzzle scientists, not as monsters or curiosities, but as living things that once occupied real environments. We will consider what it meant to live without eyes, teeth, bones, or much movement, and why those absences matter. We will see the first hints of animals pushing, creeping, disturbing the sediment, quietly introducing a new behaviour that would eventually transform the seafloor. And later, we will approach the end of this strange interval, when many Ediacaran forms disappeared, and the Cambrian world began to stir with more active, more recognisable, and frankly more troublesome animals. But for now, there is no need to hurry toward claws and shells. The Ediacaran deserves its own pace. It is not a loud period. It does not announce itself with the thunder of giant reptiles, or the glittering danger of sabre teeth. It is more like entering a dim room and waiting for your eyes to adjust. At first, everything seems still. Then shapes emerge. A frond here, a disc there, a quilted oval resting on the mat. The longer you look, the more the seafloor becomes populated, not with creatures you can easily name, but with lives that were doing something, growing somehow, responding to their world in ways that left just enough evidence to keep us wondering. And that wondering is part of the comfort. We do not have to solve every mystery at once. We can simply stay with it for a while, letting the ancient ocean become clearer in the mind. So take a slow breath and picture the Earth after ice. The sunlight is weak but returning. The oceans are open. The bare continents are being weathered by wind and water. Chemistry is shifting in the seas. Microbes are busy, as microbes always are, making a living without asking for much applause. And somewhere beneath the surface, in quiet marine places, larger forms are beginning to appear. They do not yet look like the animals we know. They do not yet behave like the bustling creatures of later oceans. But they are there, pressed close to the seafloor, lifting into the water, spreading across the mats, testing what a body can be. The planet has thawed, and in the long aftermath of ice, life is about to become visible in a way it rarely had before. The Ediacaran world begins not with a crowded ocean, not with strange, soft creatures already spread across the seafloor, but with a planet coming out of the cold. Before those quilted bodies and branching fronds appeared in the fossil record, Earth had passed through a difficult interval of deep glaciation during the Cryogenian period. The Ediacaran followed that frozen chapter, beginning around 635 million years ago. after the Marinoan glaciation ended, and lasting until the dawn of the Cambrian, around 541 million years ago, according to many summaries of the period, though modern geological charts place the Cambrian boundary very close to 539 million years ago. That small difference is not something to lose sleep over tonight. In deep time, a couple of million years can be the sort of rounding error that would still include the entire history of human civilization many times over, with room left for everyone's misplaced phone chargers. To imagine the beginning of this world, picture Earth not as the blue and green planet we know, but as something harsher, quieter, and in many places far less welcoming. The Great Ice Age that came before the Ediacaran was not just a chilly spell. It was part of a wider pattern of extreme glaciations in the Neoproterozoic, the kind of planetary cold that makes modern winter look like a polite disagreement about the thermostat. Glaciers may have reached low latitudes, perhaps even close to the tropics, and while scientists still discuss exactly how complete the ice cover was, the important point is that the planet had been through something severe. Oceans, land, atmosphere, and living microbes were all affected. The beginning of the Ediacaran is formally tied to rocks that sit above glacial deposits in South Australia, specifically a distinctive cap carbonate above Marinoan glacial sediments at Ediacaran Creek in the Flinders Ranges. It is a very geological way for a new age of life to begin, not with a trumpet, not with a sunrise, but with a layer of carbonate sitting on top of ancient evidence for ice. Cap carbonates are one of those details that sound plain at first and then become quietly remarkable the longer you sit with them. They are carbonate rock layers deposited after glaciations, and their presence above glacial deposits suggests that the planet's surface conditions changed dramatically. In simple terms, Earth thawed and the oceans responded. Imagine ice retreating from coastlines that had been locked away for immense spans of time. Imagine newly exposed rock meeting weather, rivers, and chemical reactions again. Rain and meltwater would have carried dissolved materials from continents into the sea. Carbon moved through the atmosphere and oceans. Minerals settled. Marine chemistry shifted. None of this happened on the timescale of a dramatic movie scene, where the ice cracks, the music swells, and a heroic microbe looks meaningfully into the distance. It happened over thousands and thousands of years, and then over millions more, with no narrator present to hurry it along. Earth does not mind taking its time. Still, the thaw mattered. A frozen or heavily glaciated planet limits the kinds of environments available for life. Microbial life can be wonderfully stubborn, and simple life had already survived for billions of years before the Ediacaran. But large, complex organisms need more than mere survival. They need usable habitats, chemical stability, nutrients, energy, and in many cases, oxygen. As the ice retreated and the oceans became more open, Earth began entering a state in which larger life had more room to try things. That phrase, try things, is not meant to suggest that life had a plan. Evolution is not a committee meeting with minutes and refreshments. It is variation, inheritance, environment, and time. But after the ice, the planet seems to have offered conditions in which bodies could become larger, more organised, and more visible in the rocks. Oxygen is one of the major parts of this story, though it needs to be handled carefully. It is tempting to imagine the Ediacaran as a moment when Earth simply took a great breath, and suddenly everything could grow large. The truth was probably messier. Oxygen levels had risen long before in Earth history, especially during the Great Oxidation event more than 2 billion years earlier, but the oceans and atmosphere did not instantly become modern. For much of Earth's early history, oxygen was unevenly distributed. Some environments had more, others less. Deep waters could remain oxygen poor, while shallower settings became more breathable by biological standards. During the Ediacaran, evidence points to oxygen becoming more available in ways that may have helped support larger multicellular life. But this was not like flipping on a light switch. It was more like turning a dimmer knob very slowly, then discovering that the wiring in the house was complicated, and half the rooms had their own opinions. Britannica summarises the Ediacaran environment as a time when oxygen levels rose in the atmosphere and oceans after the Marinoan glaciation, while also noting important changes in marine carbon isotopes. For animals, oxygen is especially useful because it allows cells to extract energy efficiently from food. More available oxygen can support larger bodies, more active lifestyles, and more complex tissues. But the earliest Ediacaran organisms were not necessarily active in the way later animals would be. Many of them seem to have lived quietly on or above the seafloor, with no clear mouth, no obvious gut, no legs, no claws, and very little evidence of anything we would call a busy day. Some may have absorbed nutrients directly from the water around them, some may have lived in association with microbes, some may not have been animals in the familiar sense at all. That is part of the puzzle. The environment was changing, and life responded, but not immediately by producing a crab, a fish, or anything that would look at home in a seafood restaurant, which is perhaps just as well for everyone involved. The land at this time would have seemed almost empty to us. There were no forests softening the hillsides, no grasses binding soils, no flowers waiting for insects, no birds lifting out of trees because there were no trees and no birds, and no insects to be late for anything. The continents were bare compared with modern landscapes. Microbial communities may have lived in damp places, and chemical weathering would have worked on exposed rock, but the thick biological skin that covers much of land today was absent. Without plants and roots, erosion behaved differently. Rivers carried sediment across landscapes without running through forests or meadows. Coastlines would have looked stark, perhaps beautiful in a severe way, but not alive in the green sense we know. Life's main stage was still the sea, and the sea itself was not the sea we know. It was not filled with fish, squid, crabs, corals, sea urchins, or forests of kelp. There were no whales singing in the deep, no sharks cruising the margins, no tiny larval animals drifting in the plankton with complicated futures ahead of them. The Ediacaran Ocean was a place of microbes, chemical gradients, soft-bodied organisms, and slowly emerging ecological experiments. Some waters may have been oxygenated enough for larger life, while other parts of the ocean remained low in oxygen or chemically difficult. This patchiness matters because it means the rise of complex life was not simply a global invitation written in bright letters across every shoreline. It was more local, more conditional, more dependent on particular environments where the chemistry, seafloor, and available nutrients happened to be suitable. The nutrients came from several sources. Weathering of continental rocks could deliver phosphorus and other materials into the oceans. Volcanic activity, continental breakup, mountain building, and shifting ocean circulation could all affect marine chemistry. The Ediacaran was not only biologically important, it was also geologically restless. Continents were moving, oceans were opening and closing, and the remains of older supercontinental arrangements were giving way to new configurations. These changes helped shape coastlines, basins, shallow seas, and deep water settings. Life does not evolve in a blank room. It evolves on a planet that keeps rearranging the furniture, sometimes gently, sometimes by shoving an entire continent across the floor. After the ice, the oceans may also have received pulses of nutrients that supported microbial productivity. Microbes were the quiet workers behind nearly everything. Cyanobacteria and other photosynthetic organisms had long been producing oxygen, changing chemistry and forming communities. The Ediacaran organisms that later became famous in fossil beds did not appear on a sterile stage. They appeared in a world already deeply microbial. The seafloor in many places was covered with microbial mats, layered communities of bacteria and other microorganisms that stabilize sediment like a living film. Before animals became enthusiastic burrowers and grazers, those mats could spread widely. They made the sea bottom different from later seafloors, less churned, more sealed, and in some places perhaps firm enough for soft organisms to rest upon without sinking into loose mud like a badly placed pudding. This matters for two reasons. First, microbial mats may have provided food, structure, or chemical environments for Ediacaran life. Some organisms may have grazed on them, rested on them, grown above them, or interacted with them in ways we are still trying to understand. Second, microbial mats helped preserve the impressions of soft bodies. Later in the Cambrian and after, animals burrowed through sediment so intensely that many delicate surfaces were destroyed before they could become fossils. In the Ediacaran, before that deep and constant mixing became common, whole bedding surfaces could be sealed and preserved. A soft organism could leave a shape in the sediment, and under the right conditions that shape could survive as a cast or mould. It is a strange kind of generosity from the ancient earth. The same quiet seafloors that allowed soft life to spread also helped some of it become visible to us. The first large Ediacaran organisms did not all arrive at once, and they did not all live in the same way. Some of the oldest well-known communities, such as those preserved at Mistaken Point in Newfoundland, include frond-like organisms that lived in deeper marine settings. These were not sunlit tide pool creatures waving cheerfully in shallow water. Many appear to have lived below the reach of sunlight, meaning they were not simple plants. Some were rangemorphs, branching organisms with fractal-like forms that increased their surface area. This may have helped them absorb nutrients from the surrounding water, though scientists continue to debate exactly how they fed. Research on Mistaken Point has shown that some Ediacaran organisms grew large and complex, with rangemorphs in particular sometimes reaching impressive sizes, even up to around 2 meters in some cases. That size is worth pausing over. Before the Ediacaran, life was mostly microscopic for a very long time. Not entirely simple, not unimportant, but usually small. Then, during this interval, organisms large enough to see clearly began appearing. Some were not just a few millimeters across, some were many centimeters, and a few were large enough that you could imagine standing beside them underwater, if you had a very reliable time machine and no concerns about breathing. The University of Cambridge describes this transition plainly. Before the Ediacaran, life forms were microscopic, but during the Ediacaran, large complex organisms first appeared, including rangemorphs that could grow as tall as 2 meters. Of course, large does not mean familiar. A rangemorph was not a tree, even if it looked a little fern-like. It was not seaweed, especially if it lived too deep for photosynthesis. It was not a modern sea pen, though comparisons have been made. It was an organism using a body plan that does not fit easily into the modern world. Its branching structure may have allowed it to make close contact with seawater, and if nutrients were available in the water column, that shape could be useful. This is one reason the post-ice Ediacaran Ocean is so interesting. It may have been, at least in certain settings, a place where dissolved nutrients were accessible enough that a large passive body could make a living simply by being very good at having surface area, which admittedly is not the sort of career advice one usually hears at school. The idea that some early Ediacaran organisms absorbed nutrients from surrounding water fits their lack of obvious mouths or digestive systems. This makes them very different from later animals, which often solve the problem of food by finding it, grabbing it, biting it, swallowing it, and making the entire neighbourhood more nervous. Ediacaran ecosystems, especially early ones, seem to have operated under gentler rules. That does not mean they were simple or peaceful in every respect. Microbial competition, chemical stress, space on the seafloor, and access to nutrients all mattered. But the familiar drama of predator and prey had not yet become the dominant engine of animal life. If the Cambrian would later introduce a world of shells, burrows, eyes, and more obvious pursuit, the early Ediacaran was still mostly a world of surfaces, chemistry, growth, and patience. Patience is easy to overlook because we're used to animals that move. We notice motion. A bird crosses the sky, a cat knocks something off a shelf, a spider appears in the bathroom with no invitation whatsoever. But many Ediacaran organisms may have lived without moving much, or at all, at least as adults. They grew, they occupied space, They interacted with water and sediment. They may have reproduced in ways that left patterns in fossil communities. They may have competed by growing taller or spreading differently, but they did not need to chase anything. After a planet had been through ice, the return of stable marine habitats may have favoured life that could settle in and make use of what the water delivered. This is why the phrase, "the planet began to breathe again," works best as a gentle metaphor rather than a literal claim. Earth did not breathe like an animal. It did not inhale after the ice and exhale a cloud of ready-made organisms. But its systems did open. Ice retreated. Weathering resumed across exposed rock. Oceans exchanged gases with the atmosphere. Oxygen became more important in marine environments. Carbon moved through rocks, water, air, and life. Microbes continued their patient chemical work, and over millions of years the conditions that allowed larger organisms to live became more common or more stable in certain places. The planet was not waking up all at once, it was adjusting. A useful way to picture this is not as a single global switch, but as a coastline after a storm. At first everything is disturbed. Sediment is shifted, water is cloudy, the air smells of salt and torn plants, and the beach looks unfamiliar. Then gradually systems re-establish themselves. Pools clear, small creatures return, patterns appear in the sand. The Ediacaran was something like that, except the storm had lasted on a planetary scale, and the beach was the whole Earth system. Life did not begin in the Ediacaran, not even close, but visible, complex, macroscopic life began to leave a wider and stranger record. And that record suggests that the thaw after the Marinoan glaciation was one of the great environmental turning points in the long history of living things. There were still hard limits. The Ediacaran atmosphere did not have modern oxygen levels. The oceans were not uniformly comfortable. There were likely episodes of environmental stress, including later glaciations and chemical disruptions. Some parts of the seafloor may have been unsuitable for large organisms for long intervals. And because soft-bodied life fossilizes so poorly, our picture is incomplete. We see what geology allowed us to see. The real Ediacaran biosphere was certainly larger, more varied, and more ordinary in its own time than the fossil record makes it appear. Fossils tend to preserve the unusual accidents, not the full daily routine. It is a little like trying to reconstruct someone's life from the dents in their sofa and a shopping list found under the fridge. Still, the evidence we do have is enough to show that something changed. By the middle and later parts of the Ediacaran, large soft-bodied organisms had appeared in many parts of the world. Fossils from Australia, Newfoundland, Namibia, Russia and elsewhere tell us that this was not a tiny local oddity. The forms differed between environments and through time, but the broader pattern remains. After the great glaciations, Earth entered a long interval in which macroscopic life became more prominent, more diverse, and eventually more animal-like. The official recognition of the Ediacaran period itself was important partly because it gave this interval its own place in the geological timescale, a named space between the frozen Cryogenian and the busy Cambrian. The International Union of Geological Sciences approved it in 2004, making it the first new geological period added in more than a century. And yet, from the point of view of the organisms living then, none of this had a name. There was no Ediacaran period for them, no Cryogenian behind them, no Cambrian ahead. There was only water, sediment, chemistry, light in some places, darkness in others, and the slow business of staying alive. A frond-like organism at Mistaken Point did not know it belonged near the beginning of visible complex life. A microbial mat did not know it was helping preserve future fossils. The carbonates above glacial deposits did not know they would one day mark a formal boundary in the geological timescale. These things became meaningful later when human beings began reading rocks as if they were pages, though often pages that had been folded, burned, buried, translated badly, and left outside for several 100 million years. That is part of the charm of this period. It asks us to think about recovery without drama. There is no single hero, There is no instant transformation. The Earth after the ice was a changing system, and life responded through countless small biological possibilities. A little more oxygen here, a little more habitable seafloor there, a useful body shape, a stable microbial mat, a basin where volcanic ash might bury a community quickly enough to preserve it, a shallow marine setting where sediment could record a soft impression. Over time, these small possibilities accumulated into a world that, to us, looks like the threshold of animal history. The more we slow down with it, the more the Ediacaran stops seeming like an empty prelude and begins to feel full in its own way. It was not empty, it was not waiting. It was inhabited by microbes, by early large organisms, by communities whose rules we're still trying to understand. The ice had gone, but its effects remained in the chemistry of the seas and in the rocks that defined the period's beginning. The atmosphere and ocean were changing, but not yet modern. The seafloor was alive, but not yet churned by the relentless burrowing that would later remake marine sediments. It was a world between states, not frozen anymore, not yet Cambrian, and in that in-between space, life found room to become visible. So now, with the ice behind us and the ocean open, we can let our attention drift downward, away from the bare continents and the changing air, down through seawater that may have been clear in some places and murky in others, past suspended particles and faint chemical gradients toward the bottom. There, spread across the sediment, are the microbial mats, the living surfaces that covered so much of the ancient seafloor. They are not dramatic at first glance. They do not leap, sing, flash, or stare, but they form the ground on which much of the Ediacaran story rests. Before we meet the strange bodies themselves, it helps to understand the surface beneath them, the seafloor that was less like loose modern sand and more like a living skin, soft, sticky, layered, and ready to hold the shapes of a world that had only just begun to breathe again. If you could drift down through an Ediacaran sea and settle gently near the bottom, the first thing you might notice is not an animal at all. It would not be a shell, a fin, a claw, or a curious little face peering back from the sand. It would be the seafloor itself. It would not look like the loose, pale, rippled sand we often imagine today, the sort that shifts beneath a swimmer's feet and politely hides sharp shells exactly where toes are most likely to find them. Much of the Ediacaran seafloor was covered by microbial mats, layered communities of bacteria and other microorganisms that spread across sediment like a living skin. From our point of view, it might look like a dark film, a wrinkled carpet, or a sheet of damp velvet laid over the bottom of the sea. Not velvet in the fancy theatre seat sense, of course. More like velvet designed by microbes with no interest in comfort, interior decoration, or whether it matched the curtains. These mats were made by countless tiny organisms living together in layers. Some used sunlight if they lived in shallow enough water. Some fed on chemicals. Some produced sticky substances that trapped sediment grains and helped bind the surface together. Over time, these communities formed tough, flexible coatings over the sea floor. They could wrinkle, crack, blister, fold, and trap bubbles. They could turn loose sediment into something more stable, almost like a soft crust. In many places, the bottom of the ocean would have been less like a beach and more like a living floor, textured and organised by organisms far too small to see individually. Before large animals began ploughing through marine sediment, this microbial covering could remain widespread and relatively undisturbed. It is hard to overstate how different that makes the Ediacaran world from many later seas. Today, if you visit a modern, shallow marine environment, the sediment is often worked over by animals. Worms burrow through it, clams dig into it, crabs stir it, sea cucumbers process it. Tiny creatures crawl, graze, filter, and tunnel through the grains. The sea floor is busy, even when it looks calm from above. It is like a quiet office where everyone is typing under the desk. But in the Ediacaran, before that style of animal activity became common, large parts of the seafloor could sit under microbial mats without being constantly overturned. Sediment surfaces could remain intact for longer. The mat could seal the grains, trap organic material, and create a stable place where larger soft-bodied organisms could attach, rest, or spread. It gave the ancient seafloor a different texture, a different chemistry, and a different rhythm of life. These mat-covered environments are sometimes called mat grounds. The word is not especially glamorous, but it is useful. A mat ground is a seafloor dominated by microbial mats rather than by burrowing animals or loose sediment. It is a place where microscopic life shapes the ground beneath larger life. And for the Ediacaran, mat grounds were not just background scenery, they were part of the main story. Many of the strange organisms we associate with this period lived on, in or above these mat grounds. Some may have depended on them for food, some may have used them as a stable surface, some may have grown partly embedded in them, others may have simply shared the same environment, like neighbours who never really speak but definitely notice when one of them starts spreading across the driveway. The mats also affected the chemistry of the sea floor. Microbial communities are not passive carpets, they are active biological systems. They take in substances, release substances, trap particles, and create tiny chemical gradients from the surface down into the sediment. The top layer might receive light and produce oxygen through photosynthesis, while deeper layers could be low in oxygen and full of different microbial processes. Even across a few millimeters, the conditions could change. To a large organism resting on the mat, this living surface was not just a floor, it was a chemical landscape. Nutrients, waste products, oxygen, sulfur compounds, and organic materials could all vary across the mat. Life at this scale is subtle, but subtle does not mean simple. A microbial mat is a whole city built without streets, windows, or planning permission. If you have ever seen modern microbial mats in tidal flats, salt marshes, or hot springs, you may have noticed their strange textures. Some are smooth and dark. Some are orange, green, purple, or black, depending on the organisms and minerals involved. Some look like wrinkled leather. Some form domes or small bubbles. Some peel back in sheets. These modern mats are not exact copies of Ediacaran mat grounds, because the world around them is different now, and animals often disturb them. But they give us a glimpse of how microbes can organise surfaces. They show how tiny lives, working together, can make something large enough to see and sturdy enough to change the environment around it. The Ediacaran seafloor may have been full of these kinds of surfaces, firm in some places, slimy in others, wrinkled by currents, patched by growth, and layered with microscopic activity. This matters because the organisms of the Ediacaran were mostly soft. They did not carry hard shells like many Cambrian animals. They did not leave bones. They were not likely to preserve well under ordinary conditions. Soft bodies usually collapse, decay, get eaten, or vanish into the sediment without leaving much behind. Yet Ediacaran fossils preserve delicate impressions of bodies that had no hard parts at all. The microbial mats probably helped make that possible. A soft organism lying on a mat could press into it. The mat could hold the shape long enough for sediment to cover it. Minerals could form along the surface or within the mat. A storm or volcanic ashfall could bury the community quickly. Then, with enough geological luck, the shape could be locked in place. Hundreds of millions of years later, when the rocks split along the old bedding plane, the impression would appear. Not the creature itself, but a cast of where it touched the world. Think about how unlikely that is. A soft body in shallow water or on a marine slope dies, or is buried, or is smothered by sediment. Its tissues begin to decay. Normally the details would disappear quickly. But if the body pressed against a sticky microbial mat, and if the mat resisted decay or encouraged minerals to form, and if more sediment arrived at the right moment, the outline might survive. The mat acted almost like a recording surface. Not a perfect one, of course, more like an old tape recorder left in a damp basement for 500 million years. The signal is faint, there is static. Some parts are missing, but something comes through. Paleontologists can often recognise signs that ancient seafloors were covered with microbial mats, because the rocks preserve distinctive textures. Some surfaces look wrinkled, cracked, puckered, or uneven in ways associated with mat growth and decay. There are structures called microbially induced sedimentary structures, which is a long phrase that sounds like it might need a nap halfway through. It means sedimentary features formed because microbial mats interacted with sediment, water currents, and minerals. These structures can include wrinkle marks, roll-up textures, polygonal cracks, and other patterns that suggest the sediment surface was held together by microbial life. In Ediacaran rocks, such textures often appear alongside body fossils. That pairing is a major clue. The organisms and the mat grounds were part of the same world. One of the most famous visual textures from Ediacaran bedding surfaces is sometimes called elephant skin texture. The name is very direct. The rock surface can look wrinkled and rough, like the skin of an elephant, though much flatter, and one hopes, less likely to object to being examined with a hand lens. This texture is thought to reflect microbial mat surfaces. It shows that the sediment was not simply loose mud or sand. It had a biological covering, and that covering could be preserved. When paleontologists find an Ediacaran fossil lying on or near such textured surfaces, they are not just seeing the shape of an organism, they are seeing part of the habitat itself. The fossil is not floating alone in a blank page. It is printed onto the old floor of its world. A mat ground could also influence how organisms grew. If the sediment surface was stable, soft-bodied organisms could attach more easily. Frond-like forms might anchor to the mat or sediment below it. Flat organisms could rest on top without sinking deeply. Forms that absorbed nutrients through their body surfaces may have benefited from being spread across or raised slightly above a stable surface, where water flowed past them. The mat could also provide food for organisms capable of grazing. Later in the Ediacaran, some trace fossils suggest that certain animals or animal-like organisms moved across these mats, scraping, grazing, or disturbing them. These early traces are modest, not the deep burrow systems that would become common later, but they show a changing relationship between animals and the seafloor. At first, the mat was a floor. Then, gradually, it began to become a meal, a surface to cross and eventually something to dig through. But in the earlier and middle Ediacaran, the mat ground still had power. They helped define the environment. Imagine a broad, shallow sea with low waves moving over the bottom. Light filters down if the water is shallow enough. The microbial mat catches fine sediment. Small ripples form and are held in place. Organic material gathers. A frond-like organism rises from the surface, its branching body exposed to the water. Nearby, a flatter organism lies like a ribbed oval on the mat. Elsewhere, circular holdfasts or disc-shaped impressions mark where stalked forms once attached. Nothing moves quickly. There is no sudden chase. No animal darts out to bite another. The activity is slower and less obvious. Growth, absorption, chemical exchange, microbial metabolism, gentle burial, and decay. If a modern reef is a busy market, the Ediacaran mat ground is more like a quiet workshop, where most of the tools are microscopic. This does not mean it was lifeless or dull. It only means that our usual instincts for noticing life do not work very well there. We are drawn to faces, limbs, and movement. The Ediacaran asks us to notice surfaces. It asks us to look at the ground and understand that the ground is alive. That is an unusual adjustment for a modern mind. We tend to separate landscape and organism. A rock is a rock, a floor is a floor, and the living thing is the creature sitting on top of it. But in a mat ground, the surface itself is biological. The boundary between habitat and community becomes blurry. The mat is both a place and a population. It is both the floor and many of the lives on the floor. Ediacaran organisms did not simply live in an environment. In many cases, they lived on top of a living environment. The mats may also explain why so many Ediacaran fossils look flattened. Some organisms may have been naturally flat because that body shape gave them a large surface area. Others may look flat because they were compressed during burial. paleontologists have to work carefully to distinguish original shape from preservation. A fossil impression can be misleading. A soft organism that was once three-dimensional may be preserved as a low-relief mark in stone. A body that was flexible may be distorted by current, decay, or sediment pressure. The mat can preserve fine detail, but it can also simplify. It gives us a message from the past, but not always with perfect grammar. This is why debates about Ediacaran fossils can be so lively. One scientist may look at a fossil and see an early animal. Another may see a member of an extinct group. Another may focus on how the organism was preserved and question whether certain features reflect biology or decay. When fossils lack bones, shells, mouthparts, or clear organs, interpretation becomes difficult. The mat ground is part of that interpretation. Did a ridge belong to the organism, or was it made by the mat folding around it? Was a circular mark a body, an attachment point, or a structure formed by sediment and microbes? Was a trail made by an animal moving across the mat, or by a body being dragged by current? These are not small questions. They shape how we understand the rise of animals. One of the remarkable things about Ediacaran mat grounds is that they preserve entire surfaces, not just isolated specimens. A bedding plane can reveal a community. You can see multiple organisms distributed across the old seafloor, sometimes in patterns that suggest how they lived. Larger individuals here, smaller ones there, fronds spaced across a surface, discs clustered or scattered, repeated body forms lying in association with mat textures. It is almost like looking down on an ancient neighbourhood, though one where nobody has a front door, a mailbox, or the common decency to leave a clear family tree. These surfaces allow scientists to ask ecological questions. Were organisms competing for space? Did they grow at certain depths? Were they affected by currents? Did they reproduce by releasing propagules into the water or by spreading locally? How did their communities recover after burial events? At places like Mistaken Point, fossil surfaces have captured communities that were buried by volcanic ash. That ash layer would have settled over the organisms, smothering them but preserving their positions. The result is not just a fossil collection, but a snapshot of a living sea floor. Many of the organisms there were frond-like rangemorphs, standing or lying in communities unlike anything alive today. The mat ground beneath them, combined with rapid burial, helped create the conditions for preservation. The tragedy for the organisms became a gift for geology. This is often how paleontology works, rather impolitely. The past has to go badly for someone if we're to learn about it later. In shallower settings, storms may have played a similar role. A storm could sweep sediment across a mat-covered surface, burying organisms quickly. Later, the mat and the buried bodies could influence mineral formation. Sandstone or siltstone could preserve moulds of the body surfaces. When those rocks eventually weathered out and split apart, the old seafloor would open like a book. Not a complete book, and certainly not one with helpful page numbers, but one with enough detail to make the reader lean closer. The presence of microbial mats also shaped the transition into later marine ecosystems. During the Cambrian, animals began burrowing more deeply and more frequently into sediment. This shift is sometimes called the Cambrian substrate revolution. Before it, mat grounds were common and stable. After it, sediments became more mixed, softer in some ways, more oxygenated below the surface, and much less likely to preserve delicate mat textures. Animals changed the physical structure of the seafloor. They broke up the mats, ate them, tunneled beneath them, and turned the upper sediment into a more disturbed habitat. It was a major ecological change. From the viewpoint of a microbial mat, it must have been a rather rude development. For hundreds of millions of years, microbes had done an excellent job covering surfaces, and then along came animals with digestive systems and no respect for flooring. In the Ediacaran, though, the mat grounds were still largely intact. That gave the period its particular character. It was a world where microbial life and larger soft-bodied life were closely linked. The mat stabilised the surface, provided food or nutrients, helped shape habitats, and allowed preservation. They were not glamorous, but they were essential. Without them, the Ediacaran fossil record might be far poorer. We might know much less about those strange forms. We might imagine that large life appeared more suddenly in the Cambrian, because the soft-bodied experiments before it would have left fewer traces. In a sense, microbial mats help the Ediacaran speak. There is something comforting about that, in a quiet scientific way. The smallest organisms helped preserve the largest organisms of their time. Bacteria and other microbes, which had dominated Earth for billions of years, created the surfaces on which new forms of life could appear and later be remembered. The old microbial world did not simply vanish when larger organisms evolved. It supported them, it shaped them, it recorded them. Even today, all complex life depends on microbes in countless ways, whether we like to admit it or not. We tend to give the grand titles to animals, plants, and dramatic fossils, but microbes are the long-term managers of this planet. They were here before large bodies, they were here during the Ediacaran, and they are still here now, quietly running chemical operations while we worry about emails. If you picture the Ediacaran seafloor as living velvet, it helps to keep that image practical. It was not soft fabric, it was sticky microbial structure. It trapped grains, it changed chemistry, it formed textures, it supported communities, it could be torn by currents and regrown by life, it could be buried and replaced. It was alive in layers. On top of it, some of Earth's first large organisms spread their bodies in forms that do not fit neatly into modern categories. The mat was not just scenery beneath them. It was part of why they could live as they did, and part of why we can still see them at all. So before we focus on the famous forms themselves, the quilted ovals, the branching fronds, the discs and tubes and strange repeated patterns, it is worth spending this time with the ground they lived on. The Ediacaran was not merely a period of unusual organisms, it was a period of unusual surfaces. A seafloor could hold a shape, a microbial film could become a fossil-making partner, a soft body could press into living sediment and leave a mark that would outlast mountains, climates, oceans, and every species that would later stop to wonder about it. The mat grounds made the world feel slower, firmer, and more receptive to impressions. They were the quiet record keepers of a planet just beginning to show large life. And now, with that living surface beneath us, the ancient scene becomes easier to imagine. The seafloor is not empty. It is coated, textured, and chemically active. Currents move over it. Fine particles settle onto it. Microbes grow in layered communities. Here and there, larger forms rise or rest upon it, their bodies unlike anything that would seem ordinary in a modern tide pool. Some are shaped like fronds, some like discs, some like ribbed mats. Some look as though someone pressed a soft quilted object into wet sand and then removed it very carefully. The floor is ready, the water is moving, the planet has thawed, and across this living velvet the first strange bodies of the Ediacaran begin to come into view. Across that living velvet, the first strange bodies of the Ediacaran do not arrive like the animals of later oceans. They do not burst into view with fins, shells, eyes, or restless little legs. They appear more quietly, as impressions pressed into sediment, as raised patterns on stone, as shapes that look almost familiar until you try to name them. One resembles a leaf, but it is not a leaf. Another looks like a jellyfish, but it probably was not floating freely like a jellyfish. Another lies flat and ribbed, a soft oval body with repeated segments that seem organised, and yet not quite like the segments of a worm, an insect, or anything that would fit comfortably into a modern field guide. Some are circular, some branching, some quilted, some bag-like, some so faint that they seem less like fossils and more like the memory of something the rock once dreamed about. This is where the Ediacaran begins to feel truly unfamiliar, because the forms are large enough to see, complex enough to matter, and strange enough that even after decades of study, they still refuse to stand neatly in line. At first glance, it is tempting to sort them into ordinary categories. A frond must be a plant, a disc must be a jellyfish, A ribbed oval must be a worm, a branching shape must be seaweed. The human brain likes to tidy things quickly. It sees a shape and reaches for the nearest familiar drawer, even when the drawer is labelled badly and contains 3 old batteries, a button, and a key no one remembers. Early researchers did this too, quite reasonably. When paleontologists first began describing these fossils, many compared them with living organisms that had similar outlines. A circular fossil might be called a medusoid, meaning jellyfish-like. A frond might be compared with a sea pen or algae. A bilaterally arranged form might be treated as an early animal. But the more scientists examined the details, the more difficult those comparisons became. Shape alone can be misleading, especially when the fossil is a flattened impression of a soft body that lived more than 500 million years ago in a world with very different ecological rules. The frond-like forms are among the most elegant of the Ediacaran organisms. They often look as if delicate branches were arranged along a central stalk or axis, creating a body that rises from the seafloor like a feather, a fern, or a soft underwater plume. Some had holdfasts, circular bases that anchored them to the sediment, while their branching bodies extended into the water. They can look strangely familiar because modern seas contain organisms with frond-like shapes too. Sea pens, soft corals, algae, and some colonial animals all use branching or feather-like forms. But resemblance is not identity. A fork and a rake both have prongs, but you would not want to eat soup with the wrong one. In the Ediacaran, frond-like architecture may have evolved because it was useful for increasing surface area. If an organism absorbed nutrients directly from seawater or exchanged gases and chemicals across its body, then being broad, branching, and finely divided could be a very sensible way to live. Some of these frond-like organisms belong to a group often called rangermorphs. Their bodies were built from repeated branching units, sometimes in patterns that look almost fractal, meaning similar forms are repeated at different scales. A large branch is made of smaller branches, which are made of smaller branches still. This structure creates a great amount of surface area, without requiring the organism to build a complicated set of organs inside. It is a body plan that feels mathematical, but not in a cold way. More like a snowflake if a snowflake had decided to settle on the seafloor and become quietly alive. Rangermorphs could grow in communities, sometimes in deeper water, where sunlight would not have reached them. That makes simple comparisons with plants or algae unlikely. They were not photosynthesizing like seaweed in a sunny tide pool. They were doing something else, something suited to their own time and water chemistry. The idea of feeding without a mouth may sound odd from our point of view, because most animals we know are built around the problem of getting food inside themselves. Mouths are everywhere in the animal world. Some are neat and polite, some are terrifying, and some belong to pets that believe dinner has never once been served on time. But an organism does not need to eat like a modern animal in order to be alive. Bacteria absorb substances across their surfaces. Fungi absorb nutrients from their surroundings. Many simple aquatic organisms rely heavily on exchange across body surfaces. In the Ediacaran, a large frond with enormous surface area might have made a living by absorbing dissolved organic matter, oxygen, or other substances directly from seawater. This is still debated, and it may not apply to every frond-like form, but it helps explain why bodies could be large, passive, and strangely open to the water around them. Then there are the quilted forms, perhaps the most iconic and most puzzling of all. These organisms seem divided into repeated sections like padded compartments or inflated ribs. Some look oval, some elongated, some vaguely leaf-shaped, and some almost like soft mats with regular folds. Dickinsonia is the famous example, though it deserves more attention later because it has become one of the great symbols of the Ediacaran. For now, it is enough to picture a flat, ribbed organism resting on the microbial seafloor, sometimes only a few centimetres long, sometimes much larger, with its body divided into many units that are not quite symmetrical in the familiar animal way. The sections appear offset from one side to the other, giving the body a glide reflection pattern rather than the simple mirror symmetry we might expect from many modern animals. It is the kind of detail that makes a fossil look almost understandable, then quietly takes the understanding away. Quilted bodies may have been well suited to life on a mat ground. A flat organism spread across the seafloor could maximize contact with the surface beneath it and the water above it. If it absorbed nutrients, this could be useful. If it grazed on microbial mats, a broad underside might have helped. If it relied on symbiotic microbes, a wide body might have provided space and exposure. Different scientists have suggested different possibilities, and some ideas have aged better than others. The difficult part is that these organisms left no obvious mouths, guts, limbs, or hard parts. We are trying to infer lifestyle from shape, preservation, chemistry, and context. That is rather like guessing someone's daily routine from the imprint they left in a sofa cushion, though to be fair, some sofa cushions do contain a surprisingly detailed record of human behaviour. The circular and disc-shaped fossils add another layer of confusion. For a long time, many circular Ediacaran fossils were interpreted as jellyfish, because a flattened circle in sediment naturally invites that comparison. A jellyfish washed onto a beach can leave a round impression, and some Ediacaran discs do look like that at first glance. But many of these fossils are now thought to represent something else. Some may be holdfasts, the anchoring bases of frond-like organisms. Imagine a stalked organism attached to the seafloor by a round structure. If the stalk and frond were not preserved, the holdfast alone could remain as a circular fossil. In other cases, the discs may be parts of organisms, traces of attachment, or even sedimentary structures influenced by microbial mats. The same simple shape can have several possible origins, which is why paleontology sometimes feels less like looking at a photograph and more like listening to someone describe a photograph over a poor phone connection. One famous disc form is often called aspidella. It appears as circular impressions in Ediacaran rocks and has been found in many places. At different times, fossils like these have been interpreted as jellyfish, sea anemones, holdfasts or other structures. The trouble is that a circle is not very specific. Nature makes circles easily. Bubbles, anchors, colonies, collapsed bodies, microbial features and soft organisms can all leave round marks. It is a little unfair to the fossil, really. A circle can be doing its best and still not tell you whether it was once an animal, a base, a body, or a geological accident wearing a biological-looking hat. In the Ediacaran, where preservation is unusual and bodies are soft, even a simple disc becomes a puzzle. There are also bag-like and tube-like forms. Some Ediacaran organisms appear as sacs, ribbons, cones, or tubular bodies. These may represent early animals, microbial structures, algae-like organisms, or extinct groups. Ernietta, for example, is often reconstructed as a bag-shaped organism that lived partly buried in sediment, perhaps with a folded or quilted body exposed to passing water. Other forms show tubular construction, sometimes suggesting that organisms were beginning to build more defined bodies, though not yet the mineralized shells that would later become so common. Tubes are interesting because they create boundaries. A tube has an inside and an outside. It can guide flow, it can protect, it can hold shape. In a world of soft impressions, a tube hints at a more structured way of meeting the environment, though it still may not tell us exactly what kind of living thing we are looking at. Some Ediacaran fossils show threefold symmetry, which is especially odd to modern eyes. Tribrachidium, for example, has a circular body with 3 curving arms, or ridges radiating from the centre. Most familiar animals are bilaterally symmetrical, with left and right sides, or radially symmetrical in patterns often based on 5, 4, or many repeated parts. Threefold symmetry exists in some living things in limited ways, but it is not a common blueprint for large animals. A fossil-like Tribrachidium therefore feels like a small message from a design space that later evolution did not use very often. It looks organised, not random. It looks biological, but it does not look like the beginning of a crab, a fish, or a clam. It looks like Ediacaran life being Ediacaran life, which is to say, inconvenient for anyone trying to make a simple chart. And then there are the ghostly shapes, the fossils that are faint, incomplete, or difficult to separate from the surface around them. Some appear as low ridges, some as shallow depressions. Some look like smudges until the light catches them from just the right angle. Paleontologists often photograph Ediacaran fossils with low-angle lighting because shadows reveal relief that would otherwise be invisible. A slab may look blank under ordinary light, then suddenly show a whole community when illuminated from the side. There is something pleasing about that. The fossils are not hiding exactly, but they ask to be approached gently. Blast them with flat light, and they vanish. Let the light skim across the surface, and the ancient bodies return. This is one reason the Ediacaran feels so suited to quiet attention. It rewards looking slowly. Dinosaur bones can be dramatic from across a museum hall. A mammoth tusk announces itself. A trilobite has the decency to look like an animal even when it is small. But Ediacaran fossils often require patience. You must notice relief, pattern, repetition, texture, and context. A ridge might be a body margin. A repeated unit might show growth. A circular mark might be an anchor. A wrinkled surface might be microbial matte texture. The rock becomes less like a display case and more like a landscape viewed at dusk, when details appear gradually. The first strange bodies also raise a deeper question. What counts as an animal? Today, the answer may seem obvious when we are looking at a dog, a dolphin, or a beetle. But at the base of animal history, the boundaries become less tidy. Animals are multicellular. They consume organic matter. Their cells are organised in particular ways, and most have developmental patterns that can be studied in living species. But fossils do not preserve all of that. A flat impression does not come with a label saying whether its cells had collagen, whether its embryo divided in a certain pattern, or whether it enjoyed long walks along the microbial mat. Scientists must use indirect evidence. Body symmetry, growth patterns, trace fossils, chemical residues, ecological context, and comparisons with living organisms all become part of the argument. Some Ediacaran organisms probably were animals. Others may have been close relatives of animals. Some may represent extinct branches of early multicellular life that do not fall within any living group. This is why the Ediacaran is sometimes described as containing an evolutionary experiment, though again we must be careful. Evolution does not sit at a desk testing prototypes with a little clipboard, but the period does show a range of body plans that were not all carried forward into later ecosystems. Some ways of being large and soft persisted or gave rise to later animals. Others vanished. The Ediacaran fossil record gives us a glimpse of those possibilities before the world became dominated by the more familiar designs of the Cambrian and beyond. One important thing to remember is that these organisms lived in communities. They were not isolated oddities sprinkled randomly across the sea floor. Fossil surfaces often preserve many individuals together. Fronds could stand in groups. Flat forms could occur on the same bedding planes as discs and microbial textures. Some communities were dominated by certain body types, suggesting that different environments supported different Ediacaran ecosystems. Deep water communities were not the same as shallow water ones. Older assemblages differed from younger ones. The Ediacaran was not one single scene held still for nearly 100 million years. It was a long interval with changing environments and changing life. If we compressed it into one image, we would lose the slow replacement, diversification, and disappearance that occurred across its span. Still, even with those changes, the overall impression remains one of softness and unfamiliarity. There are few clear signs of hard skeletons for most of the period. There is little evidence of active predation in the earlier Ediacaran. There are no widespread burrow systems at first. Many organisms seem to have lived on the surface rather than deep within sediment. The seafloor was still largely a mat ground world, and the bodies upon it often seemed designed for contact, exposure, or passive interaction with water rather than pursuit. This does not mean the Ediacaran was a paradise. Life is never free from competition, stress and death. But compared with the later Cambrian seafloor, it appears less churned, less armoured, and less obviously dangerous. That difference affects how we imagine the scene. In a Cambrian sea, an animal might need armour because something else has teeth, claws, grasping appendages, or at least a deeply unpleasant feeding strategy. In the Ediacaran, many organisms did not seem to require such defences. Their bodies could remain soft and exposed. They could spread across microbial mats without shells. Fronds could rise into the water without obvious armour. This may reflect a world where ecological pressures were different, where feeding was often passive or microbial, where movement was limited, and where the arms race between predator and prey had not yet transformed animal bodies. It was not a safer world in any conscious sense. Safety did not exist as an idea, but it was a world before many of the problems that later animals would solve with spikes, shells, speed, venom, jaws, and all the other inventions that make natural history both fascinating and slightly impolite. The ghostliness of Ediacaran bodies also comes from their preservation. We are not usually seeing the organism in full anatomical detail. We are seeing surfaces, outlines, moulds and impressions. Some fossils preserve the underside of an organism, others preserve the top, some preserve external texture, some may preserve collapsed structures. This can make the same kind of organism look different depending on how it was buried and what part was recorded. Paleontologists must compare many specimens to reconstruct the original body. They must ask whether a fossil that looks like a disc is really a separate organism or the attachment point of a missing frond. Whether a ribbed form was inflated, flat, flexible or firm. Whether a branching pattern represents a single individual or a colony. The Ediacaran is a lesson in humility because the evidence is beautiful, but it is rarely obedient. And yet these fossils are not just confusing, they are also surprisingly informative. Their size tells us that large bodies had evolved. Their distribution tells us that complex life had spread across marine environments. Their shapes tell us that organisms were exploring different ways to interact with water, sediment and microbial surfaces. Their preservation tells us that mat grounds played an important role. Their disappearance and replacement through time tell us that ecosystems were changing. Even when we cannot name them neatly, they still speak. They tell us that Earth before the Cambrian was not empty. It was filled with forms that were large, organised, and successful enough to leave traces across multiple continents. This is where the title of our journey begins to feel especially apt. Life on Earth still looked alien, not because it was imaginary or unnatural, but because it belonged to a world before our familiar expectations. We are used to animals with fronts and backs, mouths and guts, nervous systems and behaviours we can picture. The Ediacaran gives us bodies that may have lived by absorption, by surface contact, by slow growth across mats, by anchoring in place, by filtering or interacting with water in ways we do not fully understand. It gives us fronds that are not plants, discs that are not necessarily jellyfish, quilts that are not blankets, and impressions that are not easy answers. It shows us a planet where large life had begun to appear, but had not yet settled into the more recognisable patterns that would later fill the seas. Perhaps the most wonderful part is that these forms were not rare failures in their own time. Some of them were widespread, some grew large, some formed dense communities. They occupied real habitats for millions of years. They were not brief mistakes waiting to be erased. They were the living world. If we could visit, we might be confused, but the organisms would not be. They would simply be there, doing what their bodies allowed, responding to currents, chemistry, sediment and each other. They would have no need to explain themselves to future mammals with headlamps and notebooks. As we keep moving across the mat-covered seafloor, the shapes become more individual. The broad categories begin to gather names. Dickinsonia, the ribbed oval that has become one of the strongest candidates for an early animal. Charnia, the elegant frond that helped reveal complex life before the Cambrian. Sprigina, with its head-like end and repeated segments. suggestive and controversial in equal measure. Cambriella, perhaps a grazing animal, leaving traces that hint at movement and feeding. Tribrachidium, with its threefold pattern, quietly refusing the symmetry rules we expected. Each of these fossils is more than a strange outline. Each is a clue to what life was becoming, and also to what it might have been without the later rush towards shells, burrows, eyes, and jaws. The seafloor is no longer just a living surface. It is a gallery of forms, some famous, some obscure, all suspended in that soft interval before animal life became easier to recognise and much harder for everyone else to ignore. The longer we stay with those first strange bodies, the less they behave like a simple introduction to familiar animal life. They do not stand politely at the beginning of a textbook, each one pointing toward a modern group and saying, "I am the early version of this." They are not so cooperative. Instead, they sit in the rocks with the calm stubbornness of things that lived perfectly well before humans arrived to sort them into categories. Some seem animal-like. Some seem almost plant-like until the details disagree. Some look as if they were assembled from a biological instruction manual that later went out of print. And among all these difficult forms, a few names come up again and again, not because they solve the Ediacaran mystery neatly, but because they show just how unusual the mystery is. Dickinsonia, Charnia, Cambriella, Sprigina, Tribrachidium, and their many quiet companions are not just fossils, they are questions preserved in stone. Dickinsonia is perhaps the most famous of the Ediacaran problem fossils, partly because it looks simple at first and then becomes less simple the longer one looks at it. It is usually preserved as a flattened oval or leaf-like impression, ribbed across its body in repeated units. Some specimens are only a few centimetres long, while others are much larger, wide enough that you could not easily cover them with both hands. Its body appears divided into many segments, but they are not arranged exactly like the segments of a worm, an arthropod, or a later animal with a clear left and right side. The units on one side are offset from the units on the other, producing a pattern sometimes described as glide reflection. That phrase sounds as if it belongs in figure skating, but in this case it simply means the body parts are mirrored with a slight shift rather than matched directly. It is one of those details that tells scientists, very politely, not to get too comfortable. For decades, Dickinsonia was pulled in different directions by different interpretations. It was called a jellyfish by some, a worm by others, perhaps a lichen-like organism, perhaps a giant single-celled creature, perhaps a member of an extinct kingdom of life, perhaps an animal, perhaps something so odd that ordinary categories were more hindrance than help. This is what happens when a fossil has no bones, no shell, no obvious mouth, no eyes, no limbs, and no preserved internal organs. It leaves us with shape, growth, context, and chemistry, which can be enough to say something meaningful, but not always enough to say everything with confidence. Dickinsonia has therefore spent much of its scientific afterlife being gently passed around the room like an unusual object at a family gathering, with everyone agreeing it matters and no one completely agreeing what it is. One reason Dickinsonia has become especially important is that chemical evidence has strengthened the case that it was an animal, or at least very close to the animal side of life. Researchers reported preserved molecular traces from Dickinsonia fossils, including strain markers associated with cholesterol, a molecule strongly linked with animals. That did not make Dickinsonia suddenly grow a face, a tail, or a tiny name tag saying confirmed guest at the animal party, but it did provide some of the strongest evidence that this flat-ribbed Ediacaran organism belonged within the animal kingdom. The study described Dickinsonids as among the oldest confirmed macroscopic animals, which is a rather grand title for something that looks, to the untrained eye, a little like a quilted bath mat that had a very serious career on the seafloor. Even if Dickinsonia was an animal, it was not an animal in the brisk, mouth-first way we often imagine. Its lifestyle remains debated. Some evidence suggests it may have moved across microbial mats and fed from them, perhaps absorbing or digesting material from the underside of its body. Fossil surfaces sometimes show repeated impressions that have been interpreted as signs of movement or resting traces, as if a Dickinsonia shifted from one spot to another, leaving behind a series of soft body prints. This is not movement like a fish swimming or a crab scuttling sideways with suspicious confidence. It would have been slow, low, and quiet, but even a little movement matters. A body that can change position in search of food is doing something different from a body that simply grows where it sits. It begins to turn the sea floor from a place to be occupied into a place to be explored, even if the exploration is happening at a pace that would make a snail check its watch. Charnia gives us a very different kind of difficulty. Where Dickinsonia lies flat and ribbed, Charnia rises in the imagination as a frond. Its fossil form is elegant, a central axis with branches or ridges arranged along it, giving the appearance of a leaf, a feather, or a soft underwater fern. It was found in Charnwood Forest in England, and its recognition was historically important because it helped overturn the old expectation that Precambrian rocks did not contain large, complex fossils. Charnia is widely known as the first Precambrian macrofossil to be formally recognised from rocks of that age, and its discovery helped open the door to the wider recognition of Ediacaran life. Before fossils like this were accepted, many scientists assumed that large, complex life only appeared with the Cambrian. Charnia made that view much harder to keep. The story of Charnia also has one of those charming human details that paleontology occasionally provides, as if to remind us that great scientific changes sometimes begin with someone simply noticing something on a rock. The fossil is associated with discoveries in the 1950s by young fossil finders in Charnwood Forest, including Roger Mason, after whom Charnia masoni was named. It looked fern-like, but it came from rocks far older than any land plants, and it was preserved in a setting that did not fit a simple seaweed interpretation. That combination made it deeply inconvenient in the best scientific way. If it was not a plant and not an ordinary animal, then what was it? The answer is still not as simple as anyone might like. Charnia has been compared to sea pens, to rangermorphs, to extinct Ediacaran groups, and to forms of life that do not sit neatly among living organisms. Its body plan is organised and repeated, but not in the same way as modern fronds that only resemble it from a distance. A key point about Charnia is that its fern-like shape does not mean it photosynthesized. Some Charnia-like organisms lived in deep water settings below the reach of sunlight, so they could not have been living like algae in a bright, shallow pool. That forces us to think differently about the frond shape. Rather than being a leaf for catching light, it may have been a structure for interacting with seawater. Branching increases surface area, and surface area is useful if an organism is absorbing nutrients, exchanging gases, or relying on close contact with the surrounding water. Charnia and its relatives may have lived by a method that does not match most modern animals, quietly exposing their bodies to currents and gathering what they needed without a mouth, stomach, or visible feeding apparatus. This is not a lifestyle that makes dramatic wildlife documentaries easy. There is only so much suspense one can build around absorbing dissolved substances from seawater, though the Ediacaran seems to have managed without ratings. Charnia also makes us confront an important issue in the Ediacaran. Similar shapes can evolve for different reasons. A frond is a useful shape. It appears in plants, algae, animals, and other living systems because branching helps gather light, food, oxygen, or nutrients. So when we see a fossil frond, we should not immediately assume it belongs to one particular group. Evolution often reuses shapes when those shapes solve common physical problems. A tree, a lung, a river delta, and a sea fan all branch, but no one sensible tries to put them in the same family album. Charnia reminds us that the Ediacaran is full of bodies shaped by physics as much as ancestry. Water moved over them, nutrients diffused toward them, sediment held them. Their forms may tell us not only who they were, but how they met the conditions of their world. Cambrian feels more familiar in some ways, though only just. It is often described as slug-like or mollusk-like, with a low soft body that lived on the seafloor. Unlike Charnia, which may have stood or rested passively in the water, Kimberella seems to have been active enough to leave feeding traces. Fossils associated with it include scratch marks on microbial surfaces, suggesting that it grazed or scraped across the mat. This makes Kimberella especially important because it hints at bilateral animals, organisms with a front and back, upper and lower sides, and some directed way of moving and feeding before the Cambrian. The classic interpretation by Fedonkin and Waggoner described Kimberella as a mollusk-like bilaterian organism, though its exact relationship to mollusks remains debated. The feeding traces matter because behaviour can sometimes be more revealing than body shape. A body fossil tells us what an organism looked like, at least in outline. A trace fossil tells us something it did. Kimberella's scratch-like traces suggest an animal interacting actively with the microbial mat, perhaps scraping food from the surface. Later research on large Ediacaran bilaterian scratch traces has continued to explore these kinds of behaviours, tying them to questions about early animals and their ability to move and feed in directed ways. This is a major shift from a world of passive fronds and broad resting bodies. A grazer changes the sea floor. It does not just occupy the mat, it removes parts of it. It leaves marks. It turns the living velvet into dinner, which is one of those evolutionary developments that seems small until you are the velvet. Recent chemical work has also added to the Kimberella story. Fossils from Russia's White Sea region have been studied for traces of ancient food, with evidence suggesting that Kimberella consumed green algae and bacteria around 558 million years ago. The Natural History Museum described this as possible evidence of one of the world's oldest meals, and it supports the idea that Kimberella had a gut capable of processing food. A gut may not sound glamorous, especially if one is trying to relax before sleep, but in animal evolution it is a serious invention. It allows an organism to take food inside, break it down, absorb nutrients, and move on to the next patch of edible surface. It helps create a more active relationship with the environment. Kimberella may not have looked like a modern snail, and it may not belong neatly inside the molluscrown group, but it gives us a glimpse of animals beginning to behave like animals in a way that feels more recognisable. Sprigina is another Ediacaran form that tempts interpretation. It has a body divided into repeated units, and often appears to have a more distinct end that some researchers have compared to a head. To the eye, it can look almost like an early segmented animal, perhaps something worm-like or arthropod-like, and for that reason it has been discussed in relation to later bilaterian groups. But once again, caution walks in with sensible shoes. The segments are not necessarily true segments in the later animal sense. The body organisation may not match that of arthropods, annelids, or any familiar group. Sprigina looks suggestive, but suggestive is not the same as settled. It is the fossil equivalent of a person in the distance who may be waving at you, or may simply be adjusting a sleeve. Tribrachidium, meanwhile, refuses a different expectation. It is circular and shows threefold symmetry, with three curved arms or lobes radiating from the centre. Most animals familiar to us are bilateral or radial in other patterns, so this three-part body plan stands out. Some studies have suggested that water flow around Tribrachidium's body may have helped it feed passively, perhaps by directing particles toward particular areas. Whether or not every detail of that interpretation holds, the fossil shows that Ediacaran organisms were using body designs that later became rare or disappeared. Threefold symmetry is not impossible in life, but it did not become one of the dominant themes of large animal evolution. Tribrachidium feels like a page from a version of animal history that did not become the main addition. There are many other Ediacaran names that could be brought into this quiet gathering. Charnia discus, with a disc-like hold-fast and frond-like upper body. Ernietta, with its bag-like folded form, often reconstructed as living partly within the sediment while exposing a structure to passing water. Yorgia, another ribbed form that may have been capable of movement and left traces interpreted by some as feeding or resting marks. Parvancorina, small and shield-like, sometimes compared with the early arthropod-like forms but not securely placed. Each organism adds something, and each one complicates something. The Ediacaran does not offer a single ladder leading neatly from microbes to modern animals. It offers a branching thicket with some branches leading forward, some ending, and some still hidden in shadow. This is why classification is such a central part of the Ediacaran story. When a fossil is clearly a trilobite, it may still raise questions, but at least everyone agrees it is an arthropod. When a fossil is clearly a brachiopod, a coral or a clam, the arguments can be detailed without being existential. Ediacaran fossils often start with the existential part. Are we looking at animals, stem animals, extinct multicellular organisms unrelated to living groups, colonies, microbial structures, failed experiments, successful experiments that simply did not survive the ecological changes that followed? The difficulty comes from the absence of hard parts and the unfamiliarity of the body plans. It also comes from the fact that the early history of animals may have included forms unlike their descendants. Ancestors do not always look like simplified versions of their later relatives. Sometimes they look like something that makes modern categories feel slightly embarrassed. The phrase, creatures that refuse to fit, should not make them sound defective. They fit their own world. They may refuse to fit our categories because our categories were built mostly from living organisms and better preserved fossils from later periods. We're trying to use the anatomy of the present to interpret a time before much of that anatomy existed. It is useful, but it has limits. Dickinsonia may have been an animal, but not an animal with obvious modern organs. Charnia may have been complex and macroscopic, but not a plant, not a sea pen in the simple modern sense and not easily placed. Cambrian may have been a bilaterian grazer, perhaps mollusk-like, but not necessarily a mollusk as we would define one today. Each fossil sits near the roots of later evolutionary patterns, where the branches are close together and the labels are harder to read. There is also a quiet emotional effect in looking at these organisms. They make the history of life feel less inevitable. It is easy to imagine evolution as a straight road that leads from simple cells to fish, reptiles, mammals, and eventually a person lying in bed listening to a video about Dickinsonia, which is certainly one of evolution's more specific outcomes. But the Ediacaran reminds us that life explored many designs. Some were large and passive, some were flat and ribbed, some stood like fronds, some grazed, some may have moved in slow, simple ways. Some had symmetries that later became uncommon. The future was not obvious from the seafloor. Nothing about Charnia guaranteed a fish. Nothing about Dickinsonia promised a horse. Nothing about Cambrian announced that one day someone would invent a kettle, wait for it to boil, and feel that time itself had slowed down. The Ediacaran organisms also lived through changing environmental and ecological conditions. They were not frozen in one peaceful scene. Over millions of years, communities appeared, shifted, and disappeared. Some forms are associated with older deep-water assemblages, others with later shallow marine settings. Toward the end of the Ediacaran, more evidence appears for movement, grazing, and interactions with the sediment. The quiet, matte-ground world was beginning to change. Cambrian and similar active organisms suggest that some animals were no longer content simply to sit on the living surface. They were beginning to use it, disturb it, and perhaps compete over it in new ways. This was not yet the full Cambrian world, with widespread skeletons and complex burrowing. But the first signs of that transformation were present. The remarkable thing is that all of these organisms, from Dickinsonia to Charnia to Cambrian, were made mostly of soft tissue, and yet we know them at all. Their preservation required the right sediment, microbial mats, burial events, mineral conditions, and later exposure. A Charnia frond preserved in ancient volcanic or sedimentary layers, a Dickinsonia pressed into sandstone, a Cambrian associated with scratch marks and chemical traces. Each is a rare survival of information. None of them had any reason to leave us a record. They were not trying to become fossils. Most living things never do. They lived, died, decayed, and disappeared. Only a tiny fraction passed into stone, and an even smaller fraction weathered out at the right moment to be found by human hands. This makes their refusal to fit even more valuable. If they were easy, they would be less useful. Their strangeness forces scientists to ask better questions about what early animals were like, how body plans evolved, how ecosystems changed, and how much of life's history belongs to lineages that left no direct modern descendants. Dickinsonia asks what the earliest large animals looked like and how they fed. Charnia asks how large, complex organisms could live without sunlight or obvious mouths. Kimberella asks when animals began moving and grazing with direction. Sprigina asks how early body organization relates to later bilateral animals. Tribrachidium asks why some Ediacaran designs vanished. Together, they show that the rise of animal life was not a single event, but a long, uneven process full of forms that are partly familiar and partly beyond comparison. So the Ediacaran seafloor becomes populated not just with shapes, but with possibilities. A ribbed oval rests on a microbial mat, perhaps feeding from the surface below it. A frond rises into the water, its branching body meeting the current. A slug-like grazer scrapes at the mat and leaves marks behind. A threefold disc sits low against the sediment, letting water move around it in a pattern we can only reconstruct with models and careful guesswork. Nearby, smaller forms cluster, attach, spread, or vanish into preservation too poor for us to read. There are no eyes watching all this, at least not eyes like ours. There are no jaws snapping through the community. There is no reef noise, no fish shimmer, no shell debris crunching under waves. But there is life, and it is no longer only microscopic. It has bodies now. Strange bodies, yes, but bodies all the same. As the scene settles, the absence of familiar features becomes as important as the presence of unfamiliar ones. These organisms are not built around teeth. Most show no eyes, they leave no bones. Their worlds were shaped by soft tissues, microbial surfaces, water flow, and slow contact, rather than by the hard machinery that would later dominate animal evolution. To understand them, we have to imagine life before the tools that make animals easy to recognize. Not lifelessness, not simplicity, but a different way of being alive, one that filled the seafloor before biting, seeing, chasing, and armoring became common answers to the problem of survival. To understand life in the Ediacaran, it helps to set aside almost everything that usually makes an animal feel like an animal. Set aside teeth first, because there were no jaws snapping through these early communities in the familiar way. Set aside eyes too, because the seafloor was not yet filled with animals watching, hiding, fleeing, or planning the tiny underwater dramas that would later become so common. Set aside bones, shells, claws, spines, and armour, at least for most of the period, because the great age of hard parts had not fully begun. And perhaps most difficult of all, set aside hurry. The Ediacaran was not a fast world, not in the way later animal worlds became fast. Much of its life seems to have lived at the pace of growth, contact, chemistry, current, and slow adjustment. If the Cambrian seas would later become busy streets, the Ediacaran seafloor was more like a quiet floor at night, with nearly everything happening softly, close to the ground and without anyone honking. This does not mean the organisms were simple, in the sense of being unimportant or poorly made. That is a trap we often fall into when looking at ancient life. We see no eyes and assume blindness as a failure, no teeth and assume helplessness, no skeleton and assume incompleteness. But those features were not missing from the point of view of the organisms themselves. A Charnia did not spend its days wishing for a jaw. A Dickinsonia did not lie on the microbial mat thinking, if only I had a proper skull, all this would be more respectable. These creatures lived in a world where the usual pressures that later favoured speed, armour, and sharper senses were different. Their bodies made sense in relation to their surroundings. Many Ediacaran organisms were soft-bodied, and their body plans generally did not resemble modern animal groups, which is one reason they remain so difficult to classify. The absence of teeth is especially important because teeth are not just eating tools. They are signs of a certain kind of relationship between organisms. A tooth means that one body can grip, cut, puncture, crush, scrape, or process another body or a tough food surface in a concentrated way. Teeth belong to a world where feeding often involves force. The Ediacaran, for most of its story, does not give us much evidence for that kind of force. There were feeding relationships, of course. Life must get energy somehow, and no ecosystem is made entirely of polite neighbours sharing dissolved nutrients with good manners. But the visible record suggests a world before widespread macroscopic predation, before the seafloor became a place where many animals needed to defend themselves against being bitten, drilled, swallowed, or otherwise included in someone else's afternoon. Many Ediacaran organisms may have fed in ways that seem quiet to us. Some frond-like and modular forms may have absorbed nutrients directly from seawater across their body surfaces, an idea known as osmotrophy, although the details are still debated, and not all researchers agree on how well it explains every organism. A body with many branches or repeated units could provide a large surface area, which is useful if your way of making a living depends on exchange with the surrounding water. This may sound like a very passive lifestyle, and by modern animal standards it is, but passive does not mean ineffective. A tree does not chase sunlight. A coral does not sprint after dinner. A fungus does not need to wave a fork. Living things often succeed by being shaped well for the flow of energy and matter around them. Other Ediacaran organisms may have interacted more directly with microbial mats. Dickinsonia, for example, may have rested on or moved across the mat surface, perhaps feeding from it. Cambrian seems to have been more active, and scratch-like feeding traces associated with it suggest that some Ediacaran animals were already scraping or grazing on microbial surfaces. Research on Cambrian and its traces has made it one of the more important examples of late Ediacaran organisms behaving in a more recognisably animal-like way. But even here, we should not picture a modern snail confidently sliding through a tide pool with a full set of familiar anatomical equipment. Cambrian was animal-like, probably bilaterian, perhaps mollusk-like, but still part of a world where many basic animal features were only beginning to become clear in the fossil record. Without teeth and hard mouth parts, feeding could be slower, broader, and less visibly violent. A flat body could make contact with the mat beneath it. A frond could expose itself to currents. A low soft grazer could scrape at microbial films. A bag-like organism could sit partly in sediment and use passing water. These are not dramatic actions, but they are actions. The Ediacaran was not frozen. It was not a still life painting. It was full of biological work, only much of that work was done without the equipment that makes later animal behaviour so easy to imagine. It is rather like trying to understand a kitchen where no one has invented knives, pans or spoons yet, but dinner is somehow still happening. The absence of eyes changes the scene just as much. Eyes transform ecosystems. Once an animal can see another animal clearly, the world becomes more complicated. Prey can detect predators. Predators can aim. Mates can display. Hiding places matter. Patterns, colours, shadows, and movement become part of survival. Vision turns the environment into information. But in the Ediacaran, there is no evidence for complex eyes like those that would become important in the Cambrian and later. Many organisms likely sense their surroundings in simpler ways, if they sense them at all. They may have responded to chemical gradients, light levels, currents, contact, sediment conditions, or the presence of food. But the seafloor was not yet a place full of staring. Imagine how different that would feel. No animal watches you approach, no pupil turns. No creature freezes because it has seen a shadow pass overhead. There may be light in shallow water, but very few organisms are using it for vision in the way later animals would. The sun still matters, especially for photosynthetic microbes and shallow water chemistry, but it's not yet filling the sea with eyes. For a modern human mind, that is strangely hard to picture. We are visual creatures, and we tend to make vision the centre of experience. Even when we imagine the past, we imagine looking at it. But much of Ediacaran life may have existed in a world of touch, chemistry, flow, and surface contact rather than images. The environment was not seen so much as encountered. This may have helped keep life slow. Eyes and speed often go together. If you can see prey, it helps to move toward it. If you can see danger, it helps to move away. If predators evolve better vision, prey may evolve better escape. The whole system can begin to accelerate. Bodies become streamlined, armoured, flexible, muscular, nervous, alert. Evolution does not become faster in a conscious sense, but the ecological pressures become sharper. The Ediacaran seems to have lived before that escalation became widespread. A soft organism could rest exposed on a microbial mat because the world was not yet packed with large animals, looking for exposed soft organisms to eat. A frond could rise into the current without a skeleton, because there may have been little need to protect itself from being bitten apart by a passing grazer, with ambition and poor manners. Bones and shells tell a similar story. Most classic Ediacaran organisms were entirely soft-bodied and did not produce hard parts such as shells, teeth, or bones, although some could still grow large. This is one reason their fossils are preserved as impressions rather than as solid remains. Later animals with skeletons gave paleontologists the luxury of hard evidence, quite literally. Shells, bones, teeth and spines survive far better than soft tissues. They can be broken, transported, buried, mineralized, and still tell a clear story. Soft Ediacaran bodies required exceptional conditions to leave a mark. The fact that we know them at all is partly thanks to microbial mats and unusual preservation. They are not fossils that shout from the rock. They murmur. The rise of hard parts near the end of the Ediacaran and into the Cambrian was a major change, but it did not happen all at once or for one single reason. Some late Ediacaran organisms, such as Claudina and Namacalathus, did produce mineralized structures or skeleton-like hard parts, and Claudina in particular is famous for showing evidence of predatory borings in some specimens. That is a very important clue, because a boring hole through a shell suggests that one organism was attacking or feeding on another in a direct way. It tells us that by the very end of the Ediacaran, at least some forms of predator-prey interaction were present. The quiet world was not completely free of unpleasantness. Nature rarely is. But these late developments stand out partly because they were not yet the normal condition across the earlier Ediacaran seafloor. Claudina is worth mentioning carefully because it sits close to the changing edge of the story. It was a small, tube-forming organism with a mineralized exoskeleton, and it appears near the end of the Ediacaran. The borings in some Claudina shells have been interpreted as signs of predation, perhaps among the earliest clear evidence of animals attacking mineralized prey. This does not mean the whole Ediacaran suddenly became a battlefield full of tiny villains drilling holes in everyone. It means the ecological rules were shifting. Hard parts may have helped with support, protection, chemistry, or life in changing seas, and predation may have been one of the pressures involved. The exact causes of early biomineralization remain debated, because seawater chemistry, oxygen, ecology, development, and predation all likely played roles. For most of the classic Ediacaran forms, though, life without bones or shells shaped everything. A soft body can bend, flatten, fold, inflate, or collapse. It can spread across a surface. It can branch finely. It can maximize contact with water or mats. But it cannot easily push against the world in the same way a skeleton allows. Muscles working against hard parts can produce forceful movement. Legs need structure. Jaws need supports. Burrowing into sediment becomes easier with stronger bodies and more organized muscles. Without hard internal or external supports, many Ediacaran organisms likely lived close to the surface, moving little or not at all, growing into shapes that use the environment rather than overpowering it. This is one reason hurry seems absent. We should be cautious, because the fossil record does not preserve every behaviour. A soft organism could move and leave very little trace under some conditions, but the overall picture is still one of limited activity compared with later animal communities. There are few deep burrows in early Ediacaran rocks. There are no widespread trackways like those made later by animals with many legs or muscular bodies. The mat grounds remained relatively intact for long intervals. Many organisms appear to have been attached, resting, or only slowly mobile. If you were watching them in real time, you might need an unreasonable amount of patience, perhaps the kind usually reserved for bread dough, sleeping cats, or software updates that insist they are nearly finished. But slow life is still life. Growth is action. Reproduction is action. Chemical exchange is action. Settling on a surface, extending into a current, absorbing nutrients, dividing, releasing young, responding to sediment, tolerating burial, recovering after disturbance. These are all biological processes. They simply do not look like the animal behaviour we're used to. A frond growing upward into the water column is doing something. A Dickinsonia changing position across a mat, if that interpretation is correct, is doing something. A microbial mat rebuilding after being disturbed is doing something. The Ediacaran asks us to widen our sense of activity. Not every living world runs on chase scenes. Life without hurry also affects how communities form. If organisms do not move much, then where they settle matters enormously. A young frond or attached organism must find a suitable place, or be carried there by water, or begin life near a parent depending on its reproductive strategy. Once in place, it may grow, compete for space, and interact with currents. If food or nutrients come from the water, height and exposure matter. If nutrients come from the mat, contact matters. If reproduction happens by releasing propagules, currents matter. A quiet seafloor can still be structured by competition and opportunity. The drama is simply slow enough that a human visitor might miss it, like watching shadows change across a wall and only realizing hours later that the room has moved from morning to evening. Reproduction in the Ediacaran is another area where the absence of familiar animal machinery leaves us with clues rather than certainty. Some fossil surfaces show clusters or size patterns that may reflect how organisms reproduced or recruited into communities. Some frond-like organisms may have spread through waterborne propagules. Others may have grown in connected groups or produced new individuals nearby. Without preserved eggs, larvae, reproductive organs, or developmental stages for most forms, much remains uncertain. But the communities themselves show that these organisms were successful at making more of themselves. They lived, reproduced, and occupied habitats over long spans of time. However strange they look to us, they were not evolutionary doodles that vanished immediately. They were functioning inhabitants of their world. Their softness also means death looked different. In a later sea, a dead-shelled animal may leave a shell behind to be rolled, buried, bored, encrusted or collected by a future beachgoer who then forgets it in a coat pocket. In the Ediacaran, a dead soft organism might collapse onto the mat, decay, dissolve into the sediment, or be covered by a storm deposit. If scavengers were rare or absent in many settings, bodies might persist long enough to influence preservation. Later, evidence appears for scavenging of buried soft-bodied organisms, suggesting that animals eventually began exploiting dead bodies as a resource too. NASA's astrobiology program reported work on Ediacaran fossils from South Australia interpreted as evidence of early scavenging, showing that even before widespread active predation, ecological interactions were becoming more complex. The development of scavenging matters because it changes what a dead body means. In a world without many scavengers, a body may be mostly a decay problem for microbes and chemistry. In a world with scavengers, a body becomes food for larger organisms, and that creates new behaviours. Something must detect it, reach it, process it, and perhaps compete over it. Scavenging may sound less dramatic than predation, but it's still a step toward a more interactive ecosystem. It introduces movement toward food. It rewards sensory abilities, It alters preservation. It is the sort of quiet ecological change that can eventually make the seafloor busier, even if it begins with the simple fact that dead soft things contain nutrients and someone eventually notices. So the Ediacaran was not a single peaceful garden in which nothing ever bothered anything else. That image is too simple. There were microbial mats, soft-bodied organisms, grazers, possible scavengers, late skeletonized forms, and early signs of predation near the period's end. But compared with later seas, it was a world before many of the obvious tools of animal competition had become widespread. Most bodies were not armoured. Most did not have eyes. Most did not have teeth. Many did not show clear evidence of active locomotion. Life was experimenting with size, shape, surface area, feeding, attachment and movement, but the full machinery of modern animal ecosystems had not yet taken over. This gives the Ediacaran its particular mood. It is not empty, but it is spacious. It is not simple, but it is less visibly aggressive. It is not motionless, but it is slow. It is a world of organisms meeting their environment through surfaces rather than through faces. Bodies lie across mats, rise into currents, sit partly buried, or creep so gently that only repeated impressions in stone reveal the possibility of movement. There are no schools of fish, no hunting squid, no armoured trilobites yet combing through the sediment. There are no reefs full of jaws and hiding places. The seafloor is still open enough for softness. For a modern listener, there is something almost restful about that, though we should not mistake restfulness for ease. These organisms still faced environmental stress, burial, competition, changing oxygen levels, shifting chemistry, and the ordinary risks of being alive in a world with no guarantees. But their lives were built around different problems. How to grow large without a skeleton, how to feed without a mouth or with only simple feeding structures, how to live on a microbial surface without being buried by sediment, how to reproduce in currents, how to maintain a body in water, how to use shape instead of speed. These are not lesser problems, they are simply older ones. And as the Ediacaran continued, some of those problems began to receive new answers. A few organisms moved more clearly. Some scraped at mats. Some left trails. Some disturbed sediment. Some made tubes or hard parts. The seafloor, once held together by microbial films and occupied by mostly passive soft bodies, began to show signs of a new kind of restlessness. It was not yet the Cambrian explosion in full force. Not yet the busy world of burrows, shells, claws and eyes. But the quiet was beginning to change. Somewhere on those mat grounds an organism shifted forward, leaving a trace behind it, and that small act of movement pointed toward a very different future for life on Earth. Somewhere on that quiet, mat-covered seafloor, long before the ocean became crowded with fast swimmers and armoured little creatures, something moved, not quickly, not dramatically, not with fins slicing through the water or legs tapping across the sand. It may have been no more than a soft body shifting across a microbial surface, pressing forward, pausing, feeding, then shifting again. To us that sounds almost too small to matter. A faint trail, a disturbed patch, a scratch mark in a mat. But in the Ediacaran, movement was not just movement. It was a change in the relationship between life and the world beneath it. A creature that moves is no longer only accepting what the water brings. It can search. It can avoid. It can return. It can leave one place for another, and in doing so, it begins to turn the seafloor into a map. For much of the earlier Ediacaran, many large organisms appear to have lived in ways that did not require much locomotion. Frond-like forms could stand or lie in place, exposing their branching bodies to passing water. Flat forms could rest against microbial mats. Bag-like bodies could sit partly within sediment. Life was active, but often in the slow ways we have been tracing. Growth, absorption, chemical exchange, reproduction, and response to burial or current. There is nothing lesser about those actions. A stationary organism can still be highly successful. But the invention of directed movement created new possibilities. It meant that an organism could interact with its environment across space, not just through the surface it occupied. It could behave in a way that left a path. Trace fossils are the evidence of this. They are not the bodies of organisms, but the marks organisms made while doing something. A footprint, a burrow, a feeding scratch, a crawling trail, a resting impression, all of these are traces. In the Ediacaran, trace fossils become especially important because many of the bodies themselves were soft and hard to interpret. A body fossil tells us what something looked like at the moment it was preserved. A trace fossil tells us that something acted. It moved, fed, pushed, scraped, or disturbed sediment. Sometimes behaviour can be clearer than anatomy, which is a useful reminder that a creature is not only a shape, it is a set of actions carried out in a real place. Researchers studying early animal evolution often emphasise that the trace fossil record is one of the most useful sources for tracking the rise of animals and their behaviours. At first, the traces are simple. That is important. We do not begin with complicated networks of deep burrows or the tracks of many-legged animals marching in neat confidence across the bottom. We begin with mostly horizontal surface trails, shallow grooves, simple paths, and scratch marks related to microbial mat grounds. These early traces are not loud announcements of the Cambrian world. They are quieter than that. They show organisms interacting with the surface without yet completely overturning it. In late Ediacaran shallow marine deposits, trace fossils are often simple and rare compared with later Cambrian trace fossil assemblages, and many appear linked to animals exploiting microbial mat grounds rather than digging deeply through sediment. Imagine a soft animal moving over a mat that has grown for days, weeks, or longer across the seafloor. The mat is sticky, layered, and slightly resistant. It is not loose sand. It holds shape. When the animal moves, it may leave a groove or a ridge. If it feeds, it may scrape away part of the microbial surface. If it pauses, its body may press into the mat. If it moves again, another impression appears nearby. Later, sediment covers the surface. Minerals form. The soft body may vanish, but the action remains. A trail is a fossilized decision, although of course the animal did not think of it that way. It did not decide in words, it simply responded to food, chemistry, contact, or whatever simple sensory world it had. Still, the result is a record of behaviour. That is why even a tiny Ediacaran trail can feel so important. It is the mark of a body doing more than just being there. Cambrian gives us one of the clearest examples of this shift. Its body has often been described as mollusk-like or slug-like, though its exact place in the animal family tree remains debated. What matters here is not only the body, but the traces associated with it. Fan-shaped sets of paired scratches called Cambrian occur in Ediacaran rocks from South Australia and Russia's White Sea region. These scratches were made into microbial mats and are interpreted as systematic feeding traces, probably produced by Cambrian. The researchers who described them argued that the co-occurrence of Cambrian bodies and scratch traces supports the presence of large bilaterian animals feeding on mat grounds before the Cambrian. That is a small revolution in the sand. A creature capable of scraping at a mat is doing something very different from a frond passively meeting a current. It has a feeding surface, perhaps a feeding organ, and some ability to position itself. It may return its body or mouth part again and again across the same patch, producing repeated marks. This is not yet a world of jaws and teeth in the familiar sense, but it is a world where parts of the seafloor are being worked over by animals. The microbial mat is no longer only a living carpet, it has become a food source, and once something becomes food, other things begin to change around it. Cambrian's feeding traces also tell us something about direction. A grazer must orient itself. It must bring its feeding apparatus to the surface it is using. It must move or at least reposition itself. Direction sounds simple, but in animal evolution it is a major step. A body with a front and a back can make one end responsible for encountering the world first. That front end can become associated with sensing, feeding, and movement. Over time, this kind of organisation matters deeply. Bilaterian animals, the broad group that includes most familiar animals from worms to insects to vertebrates, are built around this directional body plan: front and back, left and right, top and bottom. The earliest bilaterians were probably simple and small, and fossils such as Icaria warriutia from South Australia have been described as rare links between the Ediacaran record and later animal life. Icaria is not spectacular in the way a large frond or a wide Dickinsonia fossil can be spectacular. It was small, worm-like, and simple. But that is exactly why it matters. The last common ancestor of bilaterian animals was not expected to be huge, armoured or dramatic. It was expected to be modest, soft and difficult to preserve. Icaria has been associated with helminthoidic knights, a simple trace fossil that records movement and sediment displacement. The body and trace together suggest a small animal capable of moving through or across the sediment in a directed way. This is the sort of creature one might easily overlook on a fossil surface, especially if one were distracted by the larger and stranger Ediacaran bodies nearby. Yet from an evolutionary point of view, the little mover may be just as important as the grand frond standing in the current. Movement requires equipment, even when the movement is slow. A body must contract muscles or muscle-like tissues. It must coordinate those contractions. It must respond to its surroundings. It needs energy, and energy brings us back to oxygen, food, and metabolism. A creature that creeps must maintain a body capable of changing shape in controlled ways. It must grip or push against the surface. It must avoid simply being carried passively by water. It may need a simple nervous system, or at least organised cellular communication. None of this needs to be complex by modern standards. We are not imagining a creature solving puzzles, or remembering where it left its reading glasses. But coordinated movement means that the body is no longer only a surface for exchange. It is a machine for action, however soft and slow that machine may be. That action could be very gentle. Peristaltic movement, the kind of wave-like contraction used by many worms and also by parts of our own digestive systems, can move a soft body without legs. A small animal can shorten and lengthen parts of itself, grip the sediment or mat, and inch forward. The result may be a simple groove or trail. A flattened organism might glide, creep, or shift by muscular waves along its underside. A grazer might anchor part of its body while scraping nearby mat. The exact mechanisms are not always known, because the fossils do not preserve muscles clearly, but the traces show that by the late Ediacaran, some organisms were doing more than settling and growing. They were crossing the surface. Dickinsonia may have joined this quiet movement, though its case is more debated. Some fossil surfaces show repeated Dickinsonia-like impressions that have been interpreted as evidence of movement and feeding from microbial mats. More recent work has described fossil structures associated with Dickinsonia that may represent motor activity, suggesting that these organisms were not always fixed in place. If that interpretation is correct, Dickinsonia was not merely a soft oval lying passively on the seafloor. It could detach, shift, and settle again. That is a strange image. A broad-ribbed body slowly relocating across a microbial mat, perhaps digesting or absorbing material from the surface beneath it, leaving behind ghostly records of where it had been. It is worth saying gently that not every proposed movement trace is accepted without debate. Ediacaran fossils are difficult, and paleontologists are careful because similar-looking structures can form in different ways. A repeated impression might be behaviour, or it might reflect current movement, decay, preservation, or sediment disturbance. This uncertainty is not a weakness of the science. It is the science working honestly with old and delicate evidence. Still, when multiple lines of evidence point toward movement, body fossils, trace fossils, feeding marks, and ecological context, the broader pattern becomes convincing. The late Ediacaran seafloor was no longer occupied only by stationary or passive forms. It contained animals capable of directed action. Tribrachidium has also been discussed in relation to possible movement traces, though it is better known for its unusual threefold body plan. Cambrian, Dickinsonia, and Tribrachidium have all been included in studies describing traces of locomotion associated with Ediacaran macroorganisms from the White Sea region. Whether each case is interpreted in exactly the same way by all researchers is less important for our larger story than the trend. The Ediacaran record begins to include behaviour. Soft bodies were not only shapes preserved by accident. Some were leaving records of where they had gone and what they had done. Once movement appears, the seafloor changes as a habitat. A stationary organism competes mostly by occupying space, growing, intercepting flow, or using the chemistry around it. A mobile organism can search for patches of food, leave depleted areas, avoid poor conditions, and perhaps respond to other organisms. Even slow movement changes the scale of life. A mat ground becomes patchy in a new way. Some areas are grazed, some are crossed, some are disturbed. The surface begins to carry a history of use. It is no longer only a continuous microbial film. It is a landscape with paths. The microbial mats themselves made these early traces possible. Because the mats stabilize sediment, a shallow trail or scratch could remain visible long enough to be buried and preserved. If the seafloor had been loose and soupy, a soft-bodied animal's path might have collapsed or vanished almost at once. The mat held the mark. It was both food and recording surface. That is one of the most interesting contradictions of the late Ediacaran. The same microbial mats that helped preserve the quiet world of soft-bodied organisms also recorded the first behaviours that would eventually help destroy mat ground dominance in shallow seas. As animals became more active, they began to disturb sediment more deeply and more often. In the Cambrian, this process expanded dramatically. Burrowing organisms mixed the upper layers of sediment, broke up microbial mats, blurred the once sharp boundary between water and seafloor, and helped create the softer, more mixed marine sediments, familiar from much of later geological history. This wider transformation is known as the Cambrian substrate revolution, or sometimes the agronomic revolution. Geological Society of America authors describe late Neoproterozoic seafloors as typically mat-covered and only weakly mixed by vertical burrowing, while Cambrian shallow marine environments increasingly lost their mat ground character as vertically oriented bioturbation became more common. But in the Ediacaran, that revolution was still gathering itself. The first movers were not yet churning the whole seafloor into a mixed layer. Many traces remained horizontal, shallow, and mat-associated. There is a great difference between grazing over a living surface and burrowing down through sediment so thoroughly that the structure of the seafloor changes. One is like leaving footprints across a rug. The other is like taking up the floorboards. The Ediacaran shows us the footprints before the floorboards started coming loose. This quiet invention of movement also changed the way bodies were built. A creature that moves directionally benefits from having a front. The front encounters the environment first. If food is ahead, the front reaches it. If danger is ahead, the front detects it. Over evolutionary time, sensory structures tend to gather there. Feeding structures may gather there too. This process, called cephalization when it becomes more developed, eventually leads to heads. But in the Ediacaran, we are looking at the very early logic behind that trend, not the finished result. A small bilaterian did not need a head like a fish or an insect. It only needed enough front-end organization to move through its world in a consistent direction. Even that was a major change. The appearance of movement also suggests new kinds of ecological information. A stationary frond does not need to know much about what lies a body length away. A moving animal does. It may need to sense chemical cues from food. It may need to distinguish mat from bare sediment. It may need to respond to oxygen levels, current, or surface texture. It may need to turn. Turning is a simple word but a meaningful behaviour. A trail that curves shows that movement was not just a body being pushed by current. It suggests active control. Some Ediacaran traces show paths that appear to meander, explore, or follow surfaces in ways that hint at basic decision-making. Not thought in the human sense, but biological response. Feeding movement would have affected microbial communities too. A grazer scraping the mat removes material and may open patches for regrowth. It can create a mosaic of disturbed and undisturbed areas. It can recycle nutrients. It can alter the surface chemistry. If many animals graze, the mat changes faster. If animals begin to burrow, the mat may not recover in the same way. This is how small behaviours become ecosystem engineering. No single tiny animal needs to intend anything. 1,000 tiny actions repeated over generations can change the physical world. There is a useful modern comparison, though it must be used cautiously. Think of earthworms in soil. A single worm is not a dramatic creature by most standards, unless one appears unexpectedly on a kitchen floor, in which case it becomes the main event. But worms mix soil, process organic matter, change drainage, and alter the structure of the ground. Their behaviour reshapes the habitat for plants, microbes, and other animals. Early marine burrowers and grazers did something comparable in ancient sediment. They changed the substrate itself. The late Ediacaran traces are the earliest hints of that coming transformation. Still, it is important not to rush the scene forward too quickly. The Ediacaran movers did not instantly replace the mat ground world. They lived within it. Cambrian needed the microbial surface it scraped. Icaria-like animals moved through or across sediment that still belonged to a mat-dominated ecosystem. Dickinsonia, if mobile, may have depended on mat surfaces for feeding. Movement began as part of the Ediacaran world before it helped usher in the next one. That makes it especially interesting. The behaviour that would later undermine the old seafloor first evolved inside it. There is something almost gentle about the earliest traces. A line across a mat, a fan of scratches, a shallow groove, a small body impression. They are not spectacular in size, yet they carry enormous meaning. They show that some organisms had begun to make choices in space. They could move toward food, across surfaces, perhaps away from unsuitable conditions. They had bodies with direction and coordination. The animal world was becoming behavioural, not just structural. A fossil frond tells us about form. A trail tells us about time. It says, here, something passed. That is also why trace fossils feel strangely intimate. A body fossil can seem like an object. A trace fossil feels like a moment. An animal moved from here to there. It paused, it scraped, it curved, it crossed an older mark. It disturbed the mat, and then the sediment sealed the action away. We are not just looking at what an organism was. We are looking at one small piece of its life. The action was brief, perhaps only minutes or hours, and yet it lasted in stone longer than mountains last in air. By the end of the Ediacaran, movement was becoming more common and more varied, though still modest compared with what followed. The seafloor was beginning to lose its old stillness. Some organisms grazed, some crawled, some may have burrowed shallowly, some produced tubes or skeletonized structures, some interacted with dead bodies, some were beginning to create traces that look forward to the Cambrian. The living velvet was being crossed, scratched, and slowly opened. Not everywhere, not all at once, but enough to signal that the rules were changing. And once those rules began changing, the older Ediacaran communities faced a different world. A mat-covered seafloor favours certain bodies, flat forms, attached forms, organisms that absorb from water or rest on stable surfaces. A churned seafloor favours others, burrowers, grazers, animals with stronger muscles, clearer direction, better senses and eventually harder parts. The first movements did not destroy the Ediacaran garden overnight, but they began to loosen its foundations. Every trail was a small interruption in the mat. Every scratch was a little removal of living surface. Every burrow, however shallow, brought the inside of the sediment into contact with the water above. The seafloor was becoming less like a sealed skin and more like a worked material. So the quiet invention of movement was not only about animals getting from one place to another, it was about the beginning of a new ecological style. Bodies became agents of disturbance. Food could be searched for rather than simply received. Sediment could be entered, surfaces could be grazed. The mat ground, once the great stabilising feature of Ediacaran life, became vulnerable to the very animals it helped support and preserve. In that slow shift, we can begin to see why the strange soft communities of the Ediacaran did not simply continue unchanged into the Cambrian. The world beneath them was being remade from the bottom up, one small trail at a time, and ahead of that changing seafloor lay the fading of many old forms and the arrival of a much busier ocean. By the late Ediacaran, the quiet seafloor was no longer quite as quiet as it had been. The living velvet was still there in many places, spread across the sediment in layered microbial films, holding the bottom together, preserving soft impressions, and providing a surface on which strange bodies could rest, rise, graze, or slowly pass. Fronds still occupied the water, flattened forms still pressed against the mat. Tubes, cups, quilted bodies, and faintly familiar animal shapes shared the seas. But something had begun to change. The old world had not vanished yet, not completely, but it was becoming less stable. The garden, if we can call it that carefully, was beginning to thin at the edges. The air and oceans were shifting. The seafloor was being scratched and crossed. Some organisms were growing harder parts, others were moving more actively. And in the fossil record, many of the classic Ediacaran forms that had once made the planet look so beautifully strange began to disappear. It is tempting to imagine this ending as a single catastrophe, a dramatic curtain falling on the old soft-bodied world just before the Cambrian burst onto the stage with claws, shells, eyes, and all the evolutionary confidence of someone entering a room wearing armour for the first time. But the real story is more complicated, and therefore more interesting. The end of the Ediacaran was not one simple event with one simple cause. Scientists have considered several overlapping explanations: environmental stress, changing oxygen levels, ocean anoxia, ecological competition, the rise of mobile animals, the spread of burrowing, the appearance of skeletons, and the possibility that some Ediacaran organisms were replaced by more active animal groups rather than wiped out in one sudden blow. Reviews of the Ediacaran Cambrian transition describe a major change in both diversity and ecosystem structure, with many members of the Ediacara biota disappearing as more familiar animal groups expanded. From the viewpoint of the organisms themselves, of course, there was no boundary line. There was no official announcement that the Proterozoic was ending and the Phanerozoic was about to begin. No one placed a neat sign on the seafloor saying, "Cambrian arriving shortly, please secure all soft-bodied lifestyles." Geological boundaries are human ways of organising rock and time. They are useful, but life experiences change as environment, reproduction, survival, and death. For an Ediacaran organism, the end may have arrived as unsuitable water, unstable sediment, a failed generation, a lost habitat, a competitor spreading nearby, a grazer scraping the mat, or a chemistry shift that made an old way of living harder to maintain. One of the strongest environmental suspects is oxygen, or rather, the lack of it in many marine settings. Oxygen had been rising in some parts of the Earth system, and oxygen availability helped make larger animals possible, but the late Ediacaran oceans were not uniformly well oxygenated. Some evidence points to major episodes of marine anoxia, meaning waters with very little dissolved oxygen, near the end of the period. Research integrating uranium isotope data with fossil evidence from rocks in South China suggested that a widespread anoxic episode coincided with the decline and disappearance of early animals in the latest Ediacaran, with modelling indicating that very large portions of the seafloor may have been overlain by oxygen-poor water. For soft-bodied organisms living on or near the seafloor, that would have mattered deeply. Oxygen is not just a helpful gas. For animals, it is tied to metabolism, size, activity, tissue function, and survival. If the water over a seafloor becomes oxygen poor, organisms that depend on oxygen may be stressed, forced away, or killed. Some Ediacaran organisms may have tolerated low oxygen better than later animals, and at least one study of a diverse Ediacaran assemblage suggests that some forms could survive intermittent low oxygen conditions, or may have colonized during brief oxygenated intervals. But tolerance has limits. A world that repeatedly shifts between usable and difficult conditions can favor some organisms while excluding others. It does not need to be a single global suffocation event to reshape life. It only has to make enough habitats unreliable for enough lineages over enough time. The phrase vanishing garden can be misleading if it suggests everything was peaceful until one terrible day. The Ediacaran was never a garden in the tidy sense. It was a set of ecosystems, changing through time, with different communities in different environments. The Avalon-type deep-water frond communities were not the same as later shallow-water assemblages in Russia, Australia, or Namibia. The Nama-style communities near the end of the period included forms such as Claudina and Namacalathus, organisms with harder parts or more structured bodies that seemed to belong to a changing ecological world. By the latest Ediacaran, the old soft-bodied communities were already sharing the planet with animals that behaved and built themselves differently. Scientific work on Claudina, for instance, describes it as one of the abundant shelled animals at the end of the Ediacaran, closely associated in some settings with microbial mat textures and showing evidence of different life modes and ecological interactions. Claudina is one of the small signs that the future was arriving early. It was not a trilobite. It was not a fish. It was not a dramatic predator cruising across the bottom in search of soft targets. It was a tube-forming organism, usually small, with a mineralized outer structure. But that mineralized tube matters. A skeleton or shell changes how an organism interacts with the world. It can provide support, it can help with attachment, it can protect against environmental stress, it can resist being eaten, it can change how the body grows. Claudina also preserves boreholes in some specimens that have been interpreted as predation marks, suggesting that by the very end of the Ediacaran, animals were beginning to interact in more direct and forceful ways. A tiny hole in a tiny tube may not sound like the beginning of a major ecological transformation. It certainly lacks the theatrical flair of a meteor impact or a volcano turning the sky dark. But in the history of animal life, a borehole can be surprisingly loud. It says that one organism may have attacked another hard-bodied organism in a focused way. It says that defences mattered. It hints that food webs were becoming more structured, that bodies were no longer just resting, absorbing, grazing, or passively filtering. There were now reasons to build walls, and once some organisms build walls, others may evolve better tools to get through them, and then still others may build thicker walls, spines, burrows, hiding behaviours, or faster bodies. This is how an arms race begins, not necessarily with a roar, but with a small problem repeated across generations. Alongside hard parts came more disturbance of the sea floor. We have already followed the earliest trails and feeding traces across microbial mats, those quiet marks of animals beginning to move. At the end of the Ediacaran and into the Cambrian, that behaviour expanded. Animals began not only crossing surfaces, but increasingly disturbing sediment vertically, mixing the boundary between water and sea floor. This transition is called the Cambrian substrate revolution. Before the Cambrian, marine seafloors in many settings were largely controlled by microbial mats. During the Ediacaran-Cambrian transition, vertical bioturbation became more important, and increased sediment mixing created new microenvironments and changed benthic ecosystems. For a mat-ground community, this was not a minor inconvenience. The microbial mat was the foundation of many Ediacaran lifestyles. It stabilized the sediment, it helped create firm surfaces, It preserved impressions. It may have provided food. It helped define the chemical boundary between water and sediment. If animals begin burrowing through that mat, breaking it, grazing it, and mixing the sediment beneath, then the old habitat begins to unravel. Imagine living on a carpet that is also your floor, your food source, your neighborhood, and the only thing keeping the basement from coming upstairs. Then imagine generations of small animals discovering that the carpet can be eaten, dug through, hidden under, and rearranged. The result is not necessarily instant destruction, but it is certainly bad news for carpet-based civilization. The shift from mat ground to mixed ground changed preservation too. Ediacaran fossils are so often visible because microbial mats help to record soft bodies. If later animals churned sediment more thoroughly, soft impressions were less likely to survive in the same way. So one question has always been whether the apparent disappearance of Ediacaran organisms partly reflects the loss of preservation conditions rather than true extinction. Maybe the organisms were still there, but the fossil record stopped recording them well. This is a sensible question. Paleontologists are always asking whether a pattern in the fossil record reflects life itself or the conditions that preserved life. The rocks can be honest, but they are not complete. They have gaps, biases, and preferences, like a very old archivist with limited shelf space. However, some evidence suggests the disappearance was not only a preservation trick. A nature communication study on the earliest Cambrian at Fortune Head in Newfoundland found that Ediacaran-style mat-ground ecology persisted into the earliest Cambrian, with conditions still capable of preserving mat-ground-related features. Yet Ediacara-type body fossils were absent above the boundary while new scratch marks became abundant. The authors argued that this points to an abrupt evolutionary event linked to the appearance of new bilaterian groups, rather than simply a slow loss of fossil preservation conditions. That does not settle every debate, but it is an important clue. If the mat grounds were still present and still able to preserve certain traces, yet the classic soft-bodied Ediacaran forms vanished from those layers, then something real likely happened to the organisms themselves. They may have gone extinct, they may have been outcompeted, they may have retreated to environments where they are harder to find. Some may have given rise to later lineages, though many probably did not. Different groups may have had different fates. The end of the Ediacaran was not necessarily one story. It may have been many endings, overlapping and uneven, like lights going out across a wide coastline one by one. Ecological replacement is one of the more subtle possibilities. It does not require a single sudden disaster. It only requires that new organisms become better suited to changing conditions. A mobile grazer can exploit microbial mats in ways a passive absorber cannot. A burrower can access food or safety beneath the surface. A skeletonized organism can resist some threats and occupy new spaces. A bilaterian with direction, feeding structures, and a stronger body can interact with the seafloor more actively. Over time, these advantages can reshape communities. The older Ediacaran forms, especially those dependent on stable mat grounds and passive feeding strategies, may have found themselves in a world where their strengths no longer match the conditions around them. This kind of replacement can feel less dramatic than extinction by catastrophe, but it can be just as final. Think of a quiet pond gradually filling with reeds, shade and silt, until the open water plants that once thrived there are no longer common. No single day needs to be fatal to everyone. The system changes and an old way of living loses its place. In the late Ediacaran the changes were larger. Ocean chemistry, oxygenation patterns, animal movement, sediment mixing, biomineralization, food webs, and perhaps predation, all shifting across millions of years. The result was a world less hospitable to many of the old soft-bodied designs. Still, it is important to resist the idea that the Cambrian simply defeated the Ediacaran. That makes evolution sound too much like a sports match, with one team wearing quilted ovals and the other team wearing shells. The Cambrian animals were not invading from elsewhere. They emerged from the same long history. The late Ediacaran already contained mobile bilaterians, grazers, skeletonized forms, and increasingly complex ecological interactions. The Cambrian explosion did not appear from an empty stage. It grew from changes already underway. The storm had clouds before it had thunder. And when the Cambrian did arrive, it did not instantly erase every trace of the old world. Some matte ground-based ecology persisted into the earliest Cambrian, even as new kinds of scratch marks, burrows and animals became more abundant. Ecosystems rarely change with perfect neatness. Old and new overlap. Some habitats preserve older styles for longer. Some organisms survive in refuges. Some behaviours spread quickly in one environment and slowly in another. The world at the boundary would have been patchy, transitional and uneven. In one basin, familiar Ediacaran textures might still dominate. In another, scratch marks and burrows might already be common. In another, chemical conditions might exclude many large organisms altogether. The disappearance of many classic Ediacaran forms is also difficult because these organisms themselves remain difficult. If we do not know exactly what Dickinsonia, Shania or many of their companions were, then explaining why they disappeared becomes harder. Were they vulnerable because they fed by absorption from seawater? Because they depended on firm microbial mats? Because they lacked mobility? Because they could not compete with grazers? Because changing oxygen levels affected their metabolism? Because their reproductive strategies failed in disturbed habitats? Several of these could be true for different organisms. The Ediacaran biota was not one kind of life. It was a collection of lineages and body plans, some likely animals, some perhaps extinct branches, all grouped together partly because they lived in the same broad interval and shared soft-bodied preservation. A single explanation may be too tidy for such a varied cast. This is one reason scientists continue to debate whether the end Ediacaran decline should be called a mass extinction. Some researchers argue that the disappearance of the Ediacara biota represents Earth's first major crisis of macroscopic complex life. Others emphasize ecological turnover, environmental change, preservation bias, or the uneven nature of the transition. A major 2023 review described the topic as an active area of research and focused on competing ideas about late Ediacaran extinctions, including the roles of ecological replacement and environmental stress. That uncertainty is not a failure. It is a sign that the event sits at the edge of what the evidence can easily reveal. We are looking through a keyhole into a room that has been gone for more than 500 million years, yet the broad pattern remains. Many of the iconic Ediacaran forms do not continue into the Cambrian. The seafloor changes. Animals become more mobile, more muscular, more directional, and more inclined to disturb sediment. Skeletons become more common. Food webs become more complex. Burrowing expands. The old mat ground world, once so important for Ediacaran ecology and preservation, becomes less dominant in shallow marine environments. The Cambrian seas were not merely filled with more animals, they were organised differently. The rules of living on the bottom had changed. There is something almost melancholy in that, but it should not be made too sentimental. Extinction is part of life's history. Most species that have ever existed are gone. Most body plans tried by life have not survived unchanged. The Ediacaran organisms did not fail in any moral sense. They lived for millions of years in environments that suited them, and then the environments and ecological pressures changed. That is how Earth works. It is not cruel in the human sense because it has no intention, but it is not gentle either. It gives time, and then conditions shift. A seafloor once perfect for soft, passive, mat-associated bodies becomes a seafloor of scratchers, burrowers, skeleton builders, and animals with increasingly complicated plans for lunch. If you imagine that late Ediacaran sea, one last time, the scene is no longer as still as it was earlier. The microbial mats remain, but they are marked. A Kimberella-like grazer has scraped fan-shaped traces into the surface. Small bilaterians have left simple trails. Tube-building organisms stand or lie among microbial textures. Some tubes carry scars or boreholes. The water chemistry may be unstable, with oxygen available in some times and places but absent in others. A familiar frond-like form may still rise from the bottom in one setting, while in another its lineage has already vanished. There are no fish yet, no trilobites in full Cambrian abundance, no coral reefs as we know them. But the ocean is becoming more animal in a modern sense, and that means it is becoming less Ediacaran. The garden vanishes not because it was imaginary, but because it was real and therefore vulnerable. Its foundations depended on microbial mats, soft bodies, and relatively low disturbance. Its organisms were shaped for surfaces, currents, and slow interactions. As movement increased, as sediment was opened, as hard parts appeared, as oxygen and ocean chemistry fluctuated, and as new ecological relationships formed, the old arrangement lost its stability. The Cambrian storm was not simply a burst of new forms, it was a reworking of habitats. It changed what the seafloor was, and therefore changed what kinds of bodies could succeed there. And after the old soft communities faded, the planet did not become less strange. It became strange in a new way. The Cambrian would bring animals with eyes, limbs, spines, shells, burrows, and appetites that left clearer marks in stone. It would bring a richer fossil record and a world that begins to look more connected to the animals we know. But something about the Ediacaran would remain singular. It was the interval when large life first became visible without yet becoming familiar. It was the time when Earth tried soft architectures that later disappeared, when microbial floors held the shapes of creatures that would not fit neatly into the future. The Cambrian may have written a louder story, but the Ediacaran left the quieter mystery underneath it, a record of life before the rules changed, before eyes looked back, before shells became common, before the seafloor was turned over and over by animals making their way through a newly restless world. What remains after the Ediacaran is not only a collection of fossils, but a change in the way we understand beginnings. Before these soft forms were recognised for what they were, it was easy to picture animal history as starting almost suddenly in the Cambrian, as if life spent billions of years quietly rehearsing in microscopic form, and then, all at once, walked onto the stage wearing shells. The Ediacaran makes that story less tidy. It tells us that large, complex life was already present before the Cambrian seas became busy with trilobites, burrows, eyes, and hard parts. By about 580 million years ago, varied seafloor organisms with frond-like, ribbon-like and quilted bodies were living in marine environments, and their fossils are now known from sedimentary rocks around the world. That is one of the first things the Ediacaran still tells us tonight. The history of life did not begin with the creatures that are easiest to recognise. It began much earlier, in forms that can feel inconvenient to our categories. We are used to fossils that behave themselves, at least a little. A tooth is usually from something with a mouth. A shell is usually from something that needed protection or support. A bone fits into a skeleton. A trilobite looks like an animal even if you have never met one before, which is probably best for both of you. But Ediacaran fossils often give us outlines without obvious organs, symmetry without clear relatives, bodies without bones, and behaviour without familiar faces. They remind us that the early history of animals was not just a smaller, simpler version of the world we know. It was a different kind of world. In a way, the Ediacaran teaches patience. Not only the patience of scientists who spend years studying faint impressions on rock slabs, though that is certainly part of it. It teaches the patience needed to look at life before it became obvious. If we rush through the Ediacaran on the way to the Cambrian, we miss the point. These organisms were not merely an opening act. They occupied real seas, formed real communities, interacted with microbial mats, responded to currents, reproduced, grew, and died. Some may have been animals, some may have been close to animals, some may have belonged to branches of complex life that left no living descendants. The uncertainty does not make them less important. It makes them more useful, because it forces us to ask what we really mean when we talk about animals, ecosystems, and complexity. Dickinsonia is a good example of this. For a long time, it was one of the great unsettled puzzles. Flat, ribbed, soft, and unlike anything alive today in a straightforward way. Then chemical evidence from ancient lipids added a powerful clue. Researchers found molecular markers associated with cholesterol in Dickinsonia fossils, supporting the interpretation that Dickinsonia was one of the earliest known macroscopic animals. That does not turn it into something familiar. It does not suddenly make Dickinsonia look like a worm, a slug, or a pancake with career ambitions, though it has been compared to several soft things over the years. What it does is show that the animal story had already begun before animals look the way we expect them to look. That matters because our own bodies are part of the same long story, though very far down the line. Not directly from Dickinsonia, perhaps, and not in any simple family album sense. But the Ediacaran belongs to the interval when large animal life, or life close to it, began taking visible form. It sits near the roots of the biological world that would eventually include fish, forests, insects, reptiles, mammals, and a sleepy listener trying to imagine a seafloor without eyes. When we look back at Ediacaran fossils, we're not looking at monsters from another planet. We are looking at Earth before the familiar pathways had narrowed. We are seeing possibilities that existed before later animal evolution made some body plans common and others disappear. The Ediacaran also reminds us that ecosystems depend on surfaces. That may sound plain, but it is easy to forget. We tend to focus on organisms themselves, especially the large or dramatic ones. We like the creature, we like the fossil, we like the named thing. But the Ediacaran world was built around mat grounds, around microbial surfaces that stabilised sediment and shaped how larger organisms lived. Those mats helped preserve the very fossils we now study. Later, as animals began to burrow and mix sediment more thoroughly, the character of the seafloor changed. The Cambrian substrate revolution describes this shift toward more disturbed marine sediment, with burrowing animals creating new microenvironments and changing the physical structure of benthic habitats. That change sounds technical, but it is really about the ground beneath life becoming different. A stable mat-covered surface favours one kind of living. A mixed, burrowed, disturbed sediment favours another. If you are a soft, flat organism that rests on microbial mats, the old seafloor suits you. If you are a small animal that can dig, search, hide and feed within the sediment, the changing seafloor offers new opportunities. The history of life is not only a history of bodies evolving, it is a history of habitats being rebuilt by the bodies that live in them. Animals did not simply adapt to the seafloor, they altered it. And once they altered it, future animals inherited a different world. There is a quiet lesson in that too. Life changes its own conditions. Microbes oxygenated parts of the planet long before animals arrived. Microbial mats shaped Ediacaran sea floors. Early grazers disturbed those mats. Burrowers opened the sediment. Plants later changed the land, soils, rivers and atmosphere. Coral reefs built habitats for countless marine species. Humans, much later and with far less excuse for not noticing, began changing the planet at a speed that would probably make a Dickinsonia retreat politely under the nearest mat if it had any way to do so. The Ediacaran is not a moral lesson by itself, but it does show that life and environment are never separate for long. Each changes the other. The Ediacaran also keeps teaching us that the fossil record is not a simple window. It is more like a set of narrow openings, each one looking into a different room, with some rooms better lit than others. Soft-bodied organisms need unusual conditions to fossilise. Microbial mats, rapid burial, mineral chemistry, and low levels of disturbance all helped preserve Ediacaran impressions. When those conditions changed, some kinds of organisms may have become harder to preserve, even if they survived for a while. This is why scientists have to be careful when asking whether the Ediacaran biota disappeared suddenly, faded gradually, moved into other habitats, or partly vanished from the record because the record itself changed, the question remains active, and researchers continue to debate the roles of environmental stress, ecological replacement, and preservation in the end Ediacaran transition. And the record is still growing. That may be the most important reason the Ediacaran still whispers to us. It is not finished. New fossil sites continue to shift the picture. In 2026, reports described new, late Ediacaran fossil discoveries in China, including the Jiangchuan biota, with hundreds of small soft-bodied specimens from roughly 546 to 539 million years ago, preserved as carbonaceous films and showing anatomical details that may push some animal complexity deeper into the Ediacaran than older views allowed. Another 2026 report described fossils from northwestern Canada that may extend the known record of complex Ediacaran animals in that region, including forms related to Dickinsonia, Kimberella, and other taxa. These discoveries matter because they make the Ediacaran less empty, less isolated, and less like a single strange exception before the real animal story begins. That is how science often works with deep time. It does not always replace one clear picture with another clear picture. Sometimes it replaces a simple picture with a richer and more difficult one. The Cambrian explosion used to look more sudden because the rocks before it seemed quieter. The more we learn from Ediacaran fossils, the more the Cambrian looks like part of a longer transition. That does not make the Cambrian unimportant. It was still a major interval of animal diversification, ecological change, biomineralization, and new behaviours. But it was not magic. The roots were already present. The Ediacaran was not a blank page before the first real sentence. It was writing in a handwriting we were only beginning to read. There is also something humbling about how much of the Ediacaran remains uncertain. We know enough to be astonished, but not enough to be finished. We can say that large soft-bodied organisms lived in Ediacaran seas. We can say that microbial mats shaped many habitats. We can say that some organisms likely moved, grazed, or absorbed nutrients. We can say that some late Ediacaran organisms had hard parts, and that ecological relationships were becoming more complex. We can say that many classic Ediacaran forms vanished before or around the rise of Cambrian-style ecosystems. But for many individual fossils, their exact relationships remain debated. That uncertainty is not a blank wall. It is a working space. It is worth thinking about what kind of evidence would make the picture clearer. Better preserved fossils can reveal anatomy. Chemical signatures can help identify biological affinities. Trace fossils can show behaviour. Sedimentology can explain habitat. Geochemistry can reconstruct oxygen levels and ocean chemistry. Developmental biology and comparisons with living animals can help us understand what early animals might have been capable of. No single clue is enough. The Ediacaran requires many kinds of evidence brought together carefully. It is not a puzzle with one missing piece. It is more like a very old shoreline scattered across continents, with some pieces preserved in Australia, some in Russia, some in Newfoundland, some in China, some in Namibia, and many still buried or eroded away. Yet even with all the uncertainty, the broad message is clear. Earth has hosted forms of life that do not fit the modern imagination. Life did not always look like the categories we use now. There were worlds before forests, worlds before skeletons, worlds before eyes became common, worlds before the seafloor was busy with burrowers. The Ediacaran gives us direct evidence of one such world. It was not empty, it was not merely waiting. It was inhabited by organisms that had their own shapes, their own ecologies, and their own long histories. That can change how we think about life elsewhere too. When people imagine alien life, they often imagine something dramatic. Eyes in strange places, tentacles, glowing forests, floating cities, or creatures with far too many opinions about human astronauts. But the Ediacaran reminds us that alien-looking life can arise right here on Earth, from ordinary evolution under unfamiliar conditions. If another planet has life, it may not look like animals we know. It may be microbial for billions of years. It may form mats, films, sheets, or structures that do not fit our favourite categories. It may become complex in ways that do not produce faces, bones, or obvious motion. The Ediacaran is a caution against expecting life to introduce itself in familiar clothing. It also makes our own time feel very brief. The Ediacaran lasted tens of millions of years. Its communities rose, changed, and disappeared across spans that dwarf human history. A fossil surface preserving a few organisms may record one moment in an ecosystem, but that ecosystem belonged to a period longer than we can easily feel. We live at the far end of the story, in a world dense with movement, sound, colour, and animal behaviour. Birds cross the sky, insects work through grass, fish move through reefs, mammals leave tracks in snow or mud, humans build cities, ask questions, and sometimes spend an evening listening to the history of creatures that had no heads. It is a strange continuity, and perhaps a comforting one. We are not separate from deep time. We are what deep time is doing right now. The Ediacaran can also soften the way we think about success and failure in evolution. Many of its organisms vanished. Some lineages may have no living descendants. Some body plans seem to have been left behind when ecosystems changed. But extinction does not mean those organisms were failures. Dickinsonia, Charnia, and the rest lived for millions of years in the conditions available to them. They were successful in their time. They did not need to lead to us to matter. That is a very useful thing to remember. The value of a life form is not measured by whether it survives to the present or becomes someone's ancestor. It is enough that it lived, interacted, reproduced, and took part in the planet's changing systems. And perhaps that is why these fossils feel so quiet. They do not demand attention the way giant bones do. They do not tower in museum halls with open jaws. They do not roar in the imagination. They lie flat, faint and patient, a ribbed oval, a branching frond, a disc, a trail, a scratch, a matte texture. Each is modest on its own, but together they change the story of life. They show us that before the ocean became a place of chase and defence, it was a place of surfaces and slow experiments. Before animals became easy to recognise, they or their close relatives were already present in forms that stretched the definition of what an animal can be. So when we say the Ediacaran still whispers, we do not have to make that mysterious in a supernatural way. The whisper is simply the evidence that survived. It is the faint relief on a slab when the light comes from the side. It is the chemical trace of ancient tissue. It is the scratch left by a grazer. It is the old microbial wrinkle preserved in stone. It is a reminder that the past is not gone completely if some part of it can still affect what we know. The organisms are gone, but their impressions remain, and those impressions continue to change how we understand the rise of life on Earth. Now, after moving through ice, oxygen, microbial mats, strange bodies, slow lives, first movements, and the fading of an old seafloor world, we come back to where we are tonight. Not in an Ediacaran sea, thankfully, because breathing would be difficult, the scenery would be confusing, and there would be nowhere comfortable to plug in a bedside lamp. We are here, in the present, with clocks, rooms, blankets, screens, and modern air moving in and out of our lungs. But somewhere beneath all this ordinary modern life is the long record that made it possible. The Ediacaran is one layer in that record, soft and strange, easy to miss, but essential to the larger story. If you are listening late at night, perhaps the room around you has gone still by now. Maybe the day has loosened. Maybe the outside world has quieted down to a low hum, or a distant car, or the small sounds a building makes when it settles into darkness. And somewhere in that quiet, it is possible to imagine another quiet, far older than any human night. A seafloor covered in microbial mats, a frond standing in the current, a flat ribbed body resting on the surface, a small animal leaving a faint trail, no voices, no birds, no waves breaking on a green shoreline, just water, sediment, chemistry, and life-taking shapes that would one day puzzle a species not yet even remotely close to existing. That is enough for tonight. The Ediacaran does not need to give us every answer. It has already given us something rarer, a view of life before it became familiar, a reminder that Earth has been stranger than our imagination, and that even the quietest fossils can carry enormous news across time. So let the ancient seafloor fade gently now, not as a closed story, but as a resting place in the mind. The mats settle, the currents move, the soft bodies leave their faint impressions. The Cambrian waits beyond the edge of the scene, but for one more moment, there is only this older world, calm, dim, and full of forms that once belonged completely to Earth, even when they still looked almost alien to us.